Hello there and welcome back to the Science Sleepy Minds. Close your eyes for a moment and picture this. You're strapping yourself into a spacecraft, the engines roar to life beneath you, and you feel the violent shudder as gravity tries to hold you down. You accelerate away from Earth faster and faster until the planet becomes a blue marble disappearing behind you. You glance at your watch. 10 hours pass. You yawn, stretch, maybe eat a freeze-dried meal or two. Then you turn around and come home. You step out of the capsule, legs wobbly, expecting your family to greet you with smiles and maybe some concern about your brief absence. But they're not there. Nobody you know is there. Because while you were gone for 10 hours, Earth aged 10 years. Your children are teenagers now. Your dog is dead. Your favourite coffee shop closed 6 years ago. And you're exactly 10 hours older, trapped in a future you never agreed to visit. That's not science fiction. That's time dilation. The one trip that turns hours into years, and it's as real as the device you're reading this on. You probably won't survive the emotional devastation, even if the physics doesn't kill you first, but hey, at least you'll be younger than your kids. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and down in the comments, tell me where you're tuning in from and what time it is for you right now. I love seeing this little global community we've built. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You've probably heard the name Albert Einstein thrown around so much it's lost meaning, like saying Kleenex when you mean tissue or Google when you mean search. But in 1905, this 26-year-old patent clerk in Bern, Switzerland, was sitting at his desk evaluating other people's inventions when his brain produced something that would crack open the universe. He wasn't in a university. He didn't have a lab. He had a thought, a pencil, and an unsettling willingness to ask what if. The question was simple. What happens to time if you're moving really, really fast? Before Einstein, time was universal. A second in London was a second in Tokyo was a second on Mars. Isaac Newton had established this back in the 1600s. Absolute time, ticking along uniformly everywhere in the cosmos like some grand cosmic metronome. You could set your watch by it, literally, and everyone everywhere would agree on what now meant. It was comforting. It was intuitive. It was completely wrong. Einstein's breakthrough came from thinking about trains, not exotic spacecraft or particle accelerators, just regular trains. Imagine you're standing on a platform and a train zooms past. At the exact moment the train passes you, lightning strikes both ends of the train simultaneously. You, standing still on the platform, see both lightning bolts at the same time because the light from each strike travels the same distance to reach your eyes. Simple enough. But here's where it gets weird. There's a passenger sitting in the exact middle of that train. From their perspective, the train is stationary and the platform is moving backward. The lightning strikes still happen, but because the train is moving forward, the passenger is actually travelling toward the light coming from the front strike and away from the light coming from the rear strike. So the passenger sees the front lightning bolt first, then the rear one a moment later. Same event. Two different observations of when it happened. Most people would shrug and say, "Sure, but we know the lightning struck at the same time, really." Einstein said, "No, there is no really. Both observations are equally valid. If the speed of light is constant for everyone, and experiments kept proving it was, then time itself must be flexible. Your now and my now are not the same thing if we're moving relative to each other. Time isn't a river flowing uniformly. It's more like taffy, stretching and compressing depending on how fast you're moving through space." The math was elegant, almost suspiciously simple. Einstein's special relativity predicted that the faster you move, the slower your clock ticks relative to someone standing still. At everyday speeds, your car, a jet plane, even the International Space Station, the effect is minuscule, nearly immeasurable. But as you approach the speed of light, about 186,282 miles per second, time dilation becomes dramatic. At 90% light speed, your clock runs at about half the rate of someone stationary. At 99.9% light speed, time slows to a crawl for you, while the universe outside ages rapidly. It's not an illusion. It's not a trick of perception. Your actual biological processes, heartbeats, thoughts, cellular decay, all slow down. You genuinely experience less time. Historians love to point out that Einstein's 1905 paper, titled On the Electrodynamics of Moving Bodies, was rejected by multiple journals initially because it seemed too radical, too detached from experimental reality. Others argue that's overstated. The paper was actually published relatively quickly in Annales de Physique, though it did take the scientific community years to fully appreciate its implications. What's undeniable is that Einstein had no experimental proof when he published it. He had logic, mathematics, and an almost arrogant confidence that the universe operated on consistent principles, even when those principles violated common sense. Historians still argue whether Einstein's genius was in the discovery itself or in his sheer audacity to believe his own equations over centuries of intuition. Here's a quirky detail that rarely makes it into textbooks. Einstein's day job reviewing patent applications actually helped him visualize relativity. He spent hours analyzing proposals for synchronizing clocks using electrical signals, which meant thinking constantly about how time measurements worked and what simultaneous really meant across distances. In a weird way, the mundane bureaucracy of the Swiss Patent Office was the perfect training ground for dismantling absolute time. Imagine if your boring desk job secretly prepared you to rewrite physics. Maybe there's hope for us all. The really unsettling part. Einstein's prediction meant you could, in theory, travel to the future. Not in a DeLorean with a flux capacitor, but simply by moving fast enough. You wouldn't need exotic matter or wormholes or paradoxes, just velocity. Get in a ship, accelerate to a significant fraction of light speed, cruise for a while, then come back. When you step out, everyone you knew would be older or dead while you'd barely aged. You'd have skipped forward in time, not by magic, but by exploiting the fundamental elasticity of space-time itself. And the universe doesn't care about your feelings. It doesn't care that you'll miss your daughter's wedding because you were travelling at 0.95 C and 10 years passed on Earth while you experienced 6 months. Physics is indifferent to heartbreak. That's the cold, beautiful terror of time dilation. It's real, it's measurable, and it's waiting for anyone bold or foolish enough to test it at scale. The moment Einstein published his theory, physicists started dreaming up scenarios to test its bizarre implications, and one thought experiment became so famous it's now known simply as the twin paradox. Picture this. You have identical twins, let's call them Anna and Elena, both 20 years old, both in perfect health, both standing in a space agency hangar staring at a sleek rocket. Anna volunteers to board the spacecraft and take a journey to a distant star system at 90% the speed of light. Elena stays on Earth, waving goodbye as her sister's rocket roars into the cosmos. From Elena's perspective, Anna is gone for 20 years. 2 decades of birthdays, holidays, technological advances, maybe a war or two, definitely several new iPhone models. But when Anna finally returns and steps out of the capsule, she's only 30 years old. She's aged 10 years. Elena, however, is now 40, with crow's feet and maybe some grey hair starting to creep in. Same DNA, same starting age, but one of them lived through twice as much subjective time as the other. You might think, wait, isn't motion relative? From Anna's perspective, Eleanor was the one moving away at 90% light speed, so shouldn't Eleanor be the younger one? That's exactly the paradox, and it stumped physicists for years because it seems like a contradiction. But here's the resolution. Anna's journey isn't symmetrical. She has to accelerate to get up to speed, decelerate to turn around at the distant star, then accelerate and decelerate again to come home. That acceleration, the change in velocity, breaks the symmetry. Anna experiences forces pushing her into her seat during those acceleration phases. Elena, sitting comfortably on Earth, ignoring the planet's own accelerations for simplicity, does not. General relativity, which extends special relativity to include acceleration and gravity, confirms that the twin who accelerates is the one who ages less. Anna genuinely experiences less time. She's a time traveller, and her older twin is the proof. The twin paradox isn't just a parlour trick for physics students. It's been experimentally verified, though not with actual human twins because, ethics committees frown on sending people on decades-long journeys just to prove a point. Instead, scientists use atomic clocks, which are so precise they can measure time differences smaller than a billionth of a second. In one famous experiment in 1971, physicist Joseph Hafele and astronomer Richard Keating flew 4 cesium beam atomic clocks around the world on commercial airplanes, eastward, then westward, while identical clocks remained at the US Naval Observatory in Washington, D.C. When they compared the clocks afterward, the flying clocks had aged slightly less than the stationary ones by nanoseconds, exactly as Einstein's equations predicted. The eastward flying clocks lost about 59 nanoseconds compared to the ground clocks, while the westward flying ones actually gained about 273 nanoseconds due to a combination of velocity and gravitational time dilation. We'll get to gravity's role shortly. The differences were tiny, but they were there, measured and undeniable. Historians love to point out that the twin paradox was first articulated not by Einstein himself, but by physicist Paul Langevin in 1911 during a lecture in Bologna. Langevin used the example of a traveller journeying at near-light speed to illustrate time dilation's practical consequences, and the scenario captured imaginations immediately. Some scholars still argue whether Langevin fully understood the resolution to the paradox or whether later physicists, including Einstein, had to clarify the role of acceleration. Either way, the thought experiment became relativity's most famous illustration, more famous, arguably, than E equals mc squared. Here's a quirky detail. Early science fiction writers seized on the twin paradox with unsettling enthusiasm. Robert A. Heinlein's 1956 novel, Time for the Stars, features literal twins communicating telepathically across light years, with one aging normally on Earth, while the other stays young aboard a relativistic starship. Joe Haldeman's The Forever War, published in 1974, explores the emotional devastation of soldiers returning from interstellar combat to find that centuries have passed on Earth, their families dead, their cultures unrecognizable, their sacrifices forgotten. These weren't just adventure stories, they were meditations on the existential horror of time dilation. You'd survive the trip, sure, but you'd lose everyone and everything you loved. Is that survival, or is it a different kind of death? The math behind the twin paradox is straightforward once you accept that time is relative. The Lorentz factor, named after physicist Hendrik Lorentz, who derived it before Einstein but didn't quite grasp its implications, determines how much time dilation occurs at a given velocity. The formula is gamma equals 1 over the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low speeds, gamma is basically 1, meaning no noticeable time dilation. At 50% light speed, gamma is about 1.15. You'd age about 15% slower. At 90% light speed, gamma jumps to 2.29. Time flows more than twice as slowly for you. At 99.9% light speed, gamma is roughly 22.4. That means 1 year for you equals 22.4 years for everyone else. You could travel to a star 50 light years away, spend a few years exploring, come home, and return to an Earth where a century has passed. Your great-grandchildren would be elderly strangers. The emotional weight of this is staggering. Imagine saying goodbye to your 5-year-old son, promising you'll be back soon, and returning when he's 65, retired, possibly resentful that you missed his entire life. Imagine falling in love, then taking a job on a relativistic cargo ship, and coming home to find your partner has been dead for 30 years. Imagine the guilt, the grief, the irreversible severance from your timeline. Some psychologists speculate that future space agencies will require time travel counselling before approving anyone for near-light speed missions, helping crew members pre-grieve the lives they're about to lose. Others think no amount of counselling could prepare you for the reality of stepping into a future where you're a relic, a curiosity, a ghost from the past who inconveniently survived. And here's the kicker. This isn't speculative. It's not maybe someday with hypothetical technology. We already know it works because we've measured it, repeatedly, with clocks and particles and satellites. The only reason we haven't sent a human on a twin paradox journey is that we don't yet have the propulsion technology to accelerate a crude spacecraft to relativistic speeds. But the physics is settled. The universe will absolutely let you time travel forward. It just won't let you come back to the moment you left. That door closes the instant you accelerate, and it never opens again. Let's get into the mechanics of how speed actually warps your clock, because understanding the why makes the what even more unsettling. You're moving right now. Yes, you, lying in bed or sitting at your desk. You're on Earth, which is spinning at about 1,000 miles per hour at the equator. Earth is also orbiting the Sun at roughly 67,000 miles per hour. The Sun itself is cruising around the Milky Way's centre at about 514,000 miles per hour, and the Milky Way is hurtling through space relative to the cosmic microwave background at around 1.3 million miles per hour. You're a passenger on a stack of nested carousels, each spinning faster than the last, and yet your coffee sits calmly in your mug and your clock ticks normally because all those velocities are relative. You don't feel motion, you feel acceleration, the change in motion. But here's the thing, all that motion does affect your clock, just imperceptibly. You're already time travelling, just not enough to notice. Special relativity tells us that time dilation depends entirely on relative velocity, how fast you're moving compared to someone else. There's no absolute reference frame, no cosmic speedometer that tells you your true speed. If you're in a windowless train moving at constant velocity, no experiment you can perform inside that train will tell you whether you're moving or stationary. This is called the principle of relativity, and it was actually first articulated by Galileo in the 1600s, though he didn't have the math to extend it to light and time. Einstein took Galileo's idea and combined it with the revolutionary finding that the speed of a light is constant for all observers, regardless of their motion. That combination, constant light speed plus no privileged reference frame, means time itself must be flexible. Here's where it gets technical but weirdly intuitive if you visualize it right. Imagine time and space as dimensions on a graph. In everyday life, you move mostly through time and barely through space. You're sitting still, spatially, and 1 hour passes, temporally. But when you start moving through space very quickly, you're essentially tilting your trajectory on that graph. You're now covering more distance through space, which means you must cover less distance through time to keep the combined space-time interval constant. This is called the space-time interval, and it's the one thing all observers agree on even when they disagree about time and distance separately. The faster you move through space, the slower you move through time. It's not that time slows down in some absolute sense. It's that your path through space-time bends, trading temporal progress for spatial progress. Physicists demonstrated this beautifully with muons, subatomic particles created when cosmic rays slam into Earth's upper atmosphere. Muons are unstable. They decay into other particles with a half-life of about 2.2 microseconds. At rest, a muon lives just long enough to travel about 660 meters before decaying. But cosmic ray muons are created about 10 kilometers up in the atmosphere and are moving at roughly 98% the speed of light. According to their short lifespans, they should decay long before reaching the ground. Yet we detect thousands of them at sea level every second. Why? Because from our reference frame, their clocks are running slow due to time dilation. At 98% light speed, their 2.2 microseconds stretch to about 15 microseconds in our frame, giving them plenty of time to reach the surface. From the muon's perspective, if we could somehow ask them, they're living exactly 2.2 microseconds, but the atmosphere is contracted, squished down to less than 700 meters thick due to length contraction, another relativistic effect. Both perspectives are valid. Both are true. The muons survive the trip to the ground because relativity bends time and space for fast-moving objects. Historians often note that this muon evidence was one of the first large-scale, naturally occurring confirmations of special relativity, observed and measured in the 1940s by physicists like Bruno Rossi. Before that, relativity was accepted mathematically, but lacked this kind of everyday, observable proof. Some textbooks claim the muon experiment was the definitive verification of time dilation, while others argue the 1971 atomic clock flights were more direct, because they involved macroscopic objects, clocks, rather than exotic particles. Historians still argue whether particle physics or precision timekeeping provided the more psychologically convincing proof for skeptics, though the physics community had moved on decades earlier. Here's a quirky tidbit. The equations of special relativity are so symmetrical that they work just as well if you swap space and time variables, a property called Lorentz invariance. This symmetry is part of why relativity feels so strange. We're used to space and time being fundamentally different things, but relativity treats them as two aspects of a single four-dimensional continuum. Hermann Minkowski, one of Einstein's former professors, formalized this geometrical interpretation of space-time in 1908, famously declaring, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Einstein was reportedly skeptical of Minkowski's geometrical approach at first, dismissing it as overly abstract, but later admitted it was essential for developing general relativity. Even geniuses need a nudge sometimes. The practical upshot of all this is straightforward. Every fast-moving object is a tiny time machine. Astronauts on the International Space Station, orbiting at about 17,500 miles per hour, age slightly slower than people on the ground, about 0.007 seconds less per 6-month mission, due to their velocity, though this is partially offset by weaker gravity at their altitude, which actually makes their clocks run faster. More on that soon. Pilots on long-haul flights, GPS satellites, particle accelerators, all are venues where time dilation is measurable and must be accounted for. The universe is constantly proving Einstein right in 1,000 small ways every day, and we've built our technology to compensate. But here's the unsettling part. There's no upper limit to how much you can dilate time as long as you keep accelerating closer to light speed. At 99.99% light speed, gamma is about 70.7. 1 year for you equals more than 70 years for Earth. At 99.9999% light speed, gamma exceeds 700. You could travel to the Andromeda Galaxy, 2.5 million light-years away, and experience the journey as just a few subjective years, while the entire history of human civilization plays out and ends back home. You'd arrive at Andromeda to find that Earth, if it still exists, has been sterilized by the sun's expansion into a red giant. You'd be the last human, alone in the universe, 1 billion generations removed from anyone you ever knew. That's the raw, indifferent power of velocity. Speed doesn't just move you through space, it moves you through time, and it doesn't ask permission. Now let's talk about gravity, because velocity isn't the only thing that messes with your clock. Mass does it too, and in some ways, gravitational time dilation is even weirder, because you don't have to be moving at all. You can be sitting perfectly still, and if you're near a massive object, a planet, a star, a black hole, time will flow slower for you than for someone farther away from that mass. This is general relativity, Einstein's 1915 expansion of his earlier theory, and it describes gravity not as a force, but as a curvature of space-time itself. Massive objects warp the fabric of the universe like a bowling ball on a trampoline, and that warping affects how time flows. The deeper you are in a gravity well, the slower your clock ticks compared to someone higher up. Here's a mind-bending fact. Your head ages faster than your feet. Yes, literally. Your head is slightly farther from Earth's centre of mass than your feet, which means it experiences fractionally less gravitational pull, which means time flows ever so slightly faster up there. Over a typical human lifetime, your head ages about 90 nanoseconds more than your feet. You'll never notice it. 90 billionths of a second is nothing. But the universe is keeping track. Atomic clocks are sensitive enough to measure this difference. In 2010, physicists at the National Institute of Standards and Technology in Colorado used state-of-the-art optical atomic clocks to detect time dilation over a height difference of just 33 centimeters, about 1 foot. Raise a clock 1 foot higher and it ticks measurably faster. The universe doesn't round. It doesn't approximate. Every millimeter of altitude matters when you're measuring time precisely enough. Einstein predicted this in his general theory of relativity, published after a decade of mind-bending mathematical labour. The theory describes gravity as the curvature of space-time caused by mass and energy. Imagine space-time as a flexible rubber sheet. Place a heavy ball, representing a star or planet, on the sheet, and it sinks, creating a depression. Smaller objects placed nearby will roll toward the depression, not because the big ball is pulling them, but because the geometry of the sheet itself is curved. That's gravity. Light travelling near the depression will follow the curve, bending its path. Time too flows slower deeper in the depression, because clocks down there are navigating a more severely curved region of space-time. This isn't a metaphor. The math describes actual geometric curvature in four-dimensional space-time, and every prediction it makes has been experimentally confirmed. One of the first confirmations came in 1959 with the Pound-Rebka experiment at Harvard University. Physicists Robert Pound and Glenn Rebka used gamma rays emitted from radioactive iron to measure the gravitational redshift, essentially the time dilation, over a vertical distance of just 22.5 meters inside a tower. They found that photons climbing out of Earth's gravitational field lost a tiny amount of energy, exactly as general relativity predicted, because they were moving from a region where time flowed slower at the bottom to one where it flowed faster at the top. The effect was minuscule, about 2.5 parts in 10 to the power of 15, but it was there. Gravity bends time, and we measured it in a university basement. Historians often point out that Einstein didn't have experimental evidence for general relativity when he published it in 1915. He derived it purely from thought experiments and mathematical consistency. The first major confirmation came in 1919 when astronomer Arthur Eddington measured the bending of starlight during a solar eclipse, but gravitational time dilation took longer to verify directly. Some scholars argue that the 1959 Pound-Rebka experiment is underappreciated in popular science narratives, overshadowed by the sexier examples like black holes and GPS satellites. Others counter that the experiment's technical complexity made it hard for the public to appreciate, unlike the dramatic imagery of bent starlight. Historians still argue whether time dilation or spatial curvature constituted the more philosophically revolutionary aspect of general relativity, both upend intuition, but in different ways. Here's a quirky detail. Einstein initially doubted whether gravitational time dilation was real or just a mathematical artifact of his equations. He went back and forth on it in letters to colleagues during 1907 and 1911, worried he'd made an error. It wasn't until he fully developed the geometrical framework of curved spacetime that he became confident the effect was physical, not just coordinate trickery. Even the person who discovered it wasn't sure at first. That should be comforting to anyone who's ever second-guessed themselves. The practical implications are profound. GPS satellites, orbiting about 20,000 kilometers above Earth, experience weaker gravity than we do on the surface. This makes their onboard clocks run about 45 microseconds per day, faster than clocks on the ground due to gravitational time dilation. At the same time, their orbital velocity of about 14,000 kilometers per hour causes their clocks to run about 7 microseconds per day slower due to velocity-based time dilation. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground-based clocks. That might sound trivial, but GPS relies on nanosecond precision. Light travels about 30 centimeters in 1 nanosecond, so even microsecond errors would cause your navigation to be off by kilometers. Every smartphone GPS chip compensates for both gravitational and velocity time dilation continuously. Without Einstein's equations programmed into the system, GPS would fail within hours. You'd miss your exit because of general relativity. Now scale this up. Imagine standing on the surface of a neutron star where gravity is so intense that space-time is warped almost beyond recognition. A neutron star crams about 1.4 times the Sun's mass into a sphere just 20 kilometers across. The gravity at the surface is roughly 200 billion times stronger than Earth's. If you could somehow survive standing there, you couldn't, you'd be crushed and vaporized instantly, but hypothetically, your clock would tick dramatically slower than one farther away. An observer watching from a safe distance would see you moving in slow motion, your words stretched into deep, incomprehensible rumbles. From your perspective, you'd feel normal, but if you looked up at the universe, everything would be sped up. Stars would race across the sky. Galaxies would evolve in fast forward. Time wouldn't stop, but the difference would be so extreme it might as well. You'd be living in a pocket of near-frozen time while the cosmos aged around you. And then there are black holes, where gravitational time dilation reaches its ultimate extreme, but we'll save that horror for later. For now, just sit with this. Gravity steals time from you. The closer you are to mass, the slower your clock runs. You can't opt out. You can't shield yourself. Gravity warps space-time, and you're made of space-time, so you warp with it. Every breath you take on Earth's surface is fractionally slower than it would be in deep space, and the universe meticulously accounts for every nanosecond of the difference. Let's nail down one of the most elegant proofs that time dilation isn't just theoretical musing. It's been measured, repeatedly, with ordinary clocks flown on ordinary airplanes. In October 1971, physicist Joseph Haffel and astronomer Richard Keating packed 4 cesium beam atomic clocks into padded cases, bought tickets on commercial flights, and literally flew around the world to test Einstein's predictions. This wasn't a multi-million-dollar space mission. It was 2 scientists with luggage full of precision instruments sitting in coach, probably annoying flight attendants with their refusal to stow the clocks during takeoff. When they returned and compared the travelled clocks with identical ones that had remained at the US Naval Observatory, the results matched Einstein's equations almost perfectly. Time dilation was no longer abstract mathematics. It was sitting in a lab in Washington, D.C., measured in nanoseconds you could count. The experiment tested both forms of time dilation simultaneously, velocity and gravity. According to special relativity, the clocks on the moving airplanes should tick slower than stationary clocks on the ground because of their velocity. But according to general relativity, the clocks at cruising altitude, about 10 kilometers up, should tick faster than ground-based clocks because they're farther from Earth's center of mass and experiencing weaker gravity. The 2 effects oppose each other, but don't cancel out completely, and their magnitudes depend on the direction of travel. Flying eastward in the direction of Earth's rotation increases the airplane's velocity relative to the non-rotating reference frame, so the velocity effect dominates and the clocks lose time. Flying westward against Earth's rotation decreases the airplane's relative velocity, so the gravitational effect dominates and the clocks gain time. When Haffel and Keating crunched the numbers, the eastward flying clocks had lost 59 nanoseconds compared to the stationary clocks, predicted 40 plus or minus 23 nanoseconds, close enough given experimental uncertainties. The westward flying clocks had gained 273 nanoseconds, predicted 275 plus or minus 21 nanoseconds, damn near perfect. The experiment wasn't flawless. There were concerns about vibration, temperature fluctuations, and the fact that cesium clocks are temperamental beasts, but independent analyses confirmed the results. Einstein was right. Time genuinely flows at different rates depending on your motion and your position in a gravitational field. You can measure it with a stopwatch, sort of, if your stopwatch is accurate to billionths of a second. Historians love to point out that the Haffel-Keating experiment was initially controversial. Some physicists questioned whether the error margins were too large, whether the flight paths were adequately controlled, whether averaging the results from 4 different clocks masked inconsistencies. Others celebrated it as a triumph of accessible experimental physics. No billion-dollar colliders, just clocks and plane tickets. The debate simmered for years until improved atomic clocks and repeated experiments in the 1970s and 1980s erased any doubt. Today, the Haffel-Keating experiment is a textbook staple, but in 1971 it was cutting-edge and contentious. Historians still argue whether the experiment's simplicity was its genius or its weakness, though the data has long since spoken for itself. Here's a quirky detail. Joseph Haffel later admitted in interviews that he was terrified the clocks would break or desynchronize during the flights, rendering the entire experiment worthless. Atomic clocks are staggeringly precise, but they're also fragile. The slightest mechanical shock can throw them off. Haffel apparently spent much of the flights hovering nervously over the clocks, ensuring they weren't jostled by turbulence or curious passengers. Imagine being seated next to a guy cradling a mysterious metal box muttering about nanoseconds. Relativity is already weird. The experiments to prove it are sometimes weirder. The real beauty of the Haffel-Keating experiment is that it made time dilation tangible. Before 1971, you could talk about atomic clocks and muons and GPS satellites, but those felt removed, technical, abstract. Flying clocks around the world on commercial airlines, though, That's something anyone can visualize. It brought relativity out of the realm of particle accelerators and into the realm of, well, vacations. You could, in theory, buy a plane ticket right now, fly continuously for a few days, and return home having aged nanoseconds less than your twin who stayed put. You'd need an atomic clock to measure the difference, and the time gain would be so small it's meaningless biologically, but it would be real. You'd be a time traveller, just a very, very slow one. And this is where the human brain struggles because we're not wired to intuit nanoseconds. 90 nanoseconds is about the time it takes light to travel 27 meters. It's 1/10,000,000th of a second. You can't perceive it. It doesn't affect your life. But stack enough of those nanoseconds together, say, by travelling at 90% light speed for a year instead of cruising at 900 kilometers per hour for a day, and suddenly you've time travelled decades. The Hafeel-Keating experiment proved the principle. The technology just hasn't caught up to the dramatic scales yet. Since 1971, physicists have repeated and refined the experiment dozens of times. In 2010, researchers at the National Institute of Standards and Technology took 2 ultra-precise optical atomic clocks, accurate to within 1 second in 3.7 billion years, and placed one just 33 centimeters higher than the other. The raised clock ticked faster by about 90 billionths of a second per day due to gravitational time dilation, 90 billionths of a second over 1 foot of altitude. If you've ever climbed a ladder, you've time-travelled forward relative to the ground beneath you. You just never notice because, well, you're not an atomic clock. The implications ripple outward. Every airplane passenger has time-travelled infinitesimally into the future. Every mountain climber has aged fractionally faster than their sea-level friends. Astronauts returning from the ISS have aged slightly less than ground control. We're all time travellers, constantly, because velocity and gravity are unavoidable. The universe doesn't grant exemptions. Einstein's equations apply to you whether you understand them or not, whether you believe them or not. The cesium clocks circling the globe in 1971 didn't care about philosophy. They just ticked slower or faster, precisely as predicted, indifferent witnesses to the malleability of time. Let's talk about the most mundane, everyday application of time dilation, the device in your pocket that tells you how to get to the nearest coffee shop. Your smartphone's GPS, or GLONASS, Galileo, Beidou, depending on which satellite constellation it's using, relies entirely on relativity. Without corrections for both gravitational and velocity-based time dilation, GPS would accumulate errors so rapidly that navigation would be useless within hours. You'd ask for directions to a restaurant and end up in someone's backyard several blocks away. The fact that GPS works, reliably, billions of times per day, is a continuous, real-time validation of Einstein's century-old theories. Every Uber driver on Earth is living proof that relativity isn't just abstract physics, it's infrastructure. Here's how it works. GPS satellites orbit about 20,200 kilometers above Earth's surface, traveling at roughly 14,000 kilometers per hour. Each satellite carries multiple atomic clocks, usually rubidium or cesium-based, that keep time to within a few nanoseconds. Your phone receives signals from at least 4 satellites simultaneously, and by comparing the timestamps encoded in those signals, it calculates your exact position. The speed of light is constant, about 300,000 kilometers per second. So if a signal from a satellite says it was sent 0.07 seconds ago, your phone knows that satellite is about 21,000 kilometers away. Triangulating signals from multiple satellites pinpoints your location. Simple in concept, but devilishly dependent on precise timing. A 1 microsecond error translates to about 300 meters of position error. GPS needs nanosecond accuracy, which means it needs to account for every factor that might desynchronize the satellite clocks from ground-based clocks, including relativity. The velocity effect comes from special relativity. The satellites are moving at 14,000 kilometers per hour relative to the surface, which means their clocks tick slower than ground clocks by about 7 microseconds per day. If that were the only factor, GPS satellites would drift out of sync, and navigation errors would accumulate at a rate of about 2 kilometers per day. Within a week, you'd miss your destination by 14 kilometers. Your GPS would tell you you're in the next town over. Chaos. But there's a second effect: gravitational time dilation from general relativity. The satellites are farther from Earth's centre of mass than you are, which means they experience weaker gravity. Weaker gravity means time flows faster. Up there in orbit, satellite clocks run about 45 microseconds per day, faster than ground clocks due to this gravitational effect. Now you've got two opposing influences: velocity slowing the clocks by 7 microseconds per day, and weaker gravity speeding them up by 45 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. Left uncorrected, GPS would accumulate about 10 kilometers of error per day, catastrophic for navigation. So engineers program the satellite clocks to tick slightly slower than ground clocks before they launch. Specifically, the satellite's clock frequencies are adjusted from 10.23 MHz, the standard ground-based frequency, to 10.22999999543 MHz. That tiny fractional adjustment compensates for the relativistic effects over the satellite's operational life. Once in orbit, the satellite clocks, now running in a different gravitational and velocity regime, tick at the same rate as ground clocks when measured from Earth's surface. Problem solved. You tap Navigate to Starbucks, and relativity, invisibly woven into the system's firmware, guides you there with meter-level precision. Historians often note that when the first GPS satellites were launched in the late 1970s, some engineers were skeptical that relativistic corrections would be necessary. The effects seemed so small, microseconds per day, that maybe the system could tolerate the errors. But early tests proved otherwise. Without corrections, GPS accuracy degraded rapidly. A 1977 paper by physicist Neil Ashby laid out the mathematics in exhaustive detail, and by the time the full GPS constellation was operational in 1995, relativistic corrections were baked into every satellite's design. Some textbooks claim that GPS was the first large-scale engineering system to require general relativity for proper functioning, while others point out that particle accelerators and astronomical observations had already relied on relativity for decades. Historians still argue whether GPS represents a philosophical milestone, relativity as everyday technology, or just another incremental application of well-established physics. Here's a quirky tidbit. The first atomic clocks flown in space weren't for GPS at all. They were part of the 1976 Gravity Probe A experiment, which launched a hydrogen master clock on a suborbital rocket to test gravitational time dilation. The clock flew to an altitude of about 10,000 kilometers, experienced weaker gravity for a couple of hours, then returned to Earth. When scientists compared its reading to ground-based clocks, they found it had gained time exactly as general relativity predicted, confirming the effect to within 0.01% accuracy. That experiment paved the way for GPS engineers to confidently design relativistic corrections into the satellite system. Sometimes you have to prove the universe works the way you think before you bet billions of dollars on it. The really unsettling part is how casually we've integrated relativity into daily life without noticing. You don't think, "Thank you, Einstein," when Google Maps reroutes you around traffic. You don't contemplate space-time curvature while ordering a rideshare. But every single satellite-based navigation system on Earth, civilian GPS, military GPS, Russia's GLONASS, Europe's Galileo, China's Beidou, relies on relativistic corrections. Airplane autopilots, shipping logistics, precision agriculture, geological surveying, even the timestamps on financial transactions, all depend on clocks synchronized across different altitudes and velocities, which means they all depend on accounting for time dilation. If relativity were wrong, modern civilization would grind to a confused halt. Trucks would get lost, planes would drift off course, your food delivery would arrive 3 neighborhoods away. Every time your phone tells you to turn left in 200 meters, it's calculating your position using signals from satellites that are time-traveling relative to you. The satellites are aging faster, and your phone knows it, compensates for it, and uses that relativistic difference to pinpoint where you are on a spinning, orbiting planet, hurtling through space. You're navigating with time dilation. You're using relativity as casually as you use a light switch, and you probably never realized it. That's the quiet triumph of modern physics. It works so well, so seamlessly, that it becomes invisible, but the universe is still keeping track, counting every nanosecond, every curve in space-time, every tick of a clock flying overhead at 14,000 kilometers per hour. Now let's bring this down to human scale. Actual people who've time-traveled measurably by living in orbit. Astronauts aboard the International Space Station aren't just floating around conducting experiments and posting Instagram photos of Earth. They're also aging slightly slower than the rest of us due to their orbital velocity, making them the closest thing we have to real-life time travelers. The effect is tiny, fractions of a second over months in space, but it's real, measurable, and scientifically fascinating. And the person who holds the record for the most accumulated time dilation, that's Russian cosmonaut Sergei Krikalev, who spent a cumulative 803 days in space over multiple missions. When he finally retired from spaceflight, he had aged about 0.02 seconds less than if he'd stayed on Earth. He's the most time-travelled human in history, though his prize is 20 milliseconds of youth he'll never notice. Let's do the math. The ISS orbits at an altitude of roughly 400 kilometers, travelling at about 7.66 kilometers per second. That's roughly 27,600 kilometers per hour, or 17,150 miles per hour. At that velocity, special relativity predicts that time dilation will slow the astronauts' clocks relative to people on the ground. Using the Lorentz factor, we calculate gamma for 7.66 kilometers per second, which comes out to about 1.0000000003. That tiny number means that for every second that passes on the ISS, about 0.999999997 seconds pass on Earth. The difference is minuscule, but over days, weeks, and months it adds up. For a 6-month ISS mission, about 180 days, velocity-based time dilation accounts for roughly 0.007 seconds of age difference. But wait, there's also gravitational time dilation working in the opposite direction. The ISS is farther from Earth's centre of mass than we are, so it experiences weaker gravity. Weaker gravity means time flows faster up there. This gravitational effect actually dominates over the velocity effect. The net result is that astronauts on the ISS age slightly faster than people on Earth, not slower, by about 0.0000003 seconds per second. Over a 6-month mission, this works out to about 0.01 seconds of extra aging due to weaker gravity, which almost cancels out the 0.007 seconds saved from velocity. The net result is that ISS astronauts age very slightly faster, by about 0.003 seconds per 6-month mission, though the exact value depends on precise orbital parameters and varies slightly mission to mission. Okay, so I lied a little. Most ISS astronauts don't time travel backward. But here's the catch. Astronauts on lower, faster orbits, or on missions to the moon, which involved higher velocities, do age less. The Apollo astronauts travelling to the moon and back at speeds approaching 11 kilometers per second experienced slightly more velocity-based time dilation, though the missions were so short, about a week, that the total effect was still just microseconds. And Sergei Krikalev spent much of his career aboard the Mir space station, which orbited slightly lower and faster than the ISS. His cumulative time dilation, factoring in both velocity and altitude effects across multiple missions, works out to about 0.02 seconds less aging than if he'd remained on Earth. He's travelled 20 milliseconds into the future. That's about the duration of a single frame in a 50 frames per second video. You literally wouldn't blink and miss it, but it's there, recorded, undeniable. Historians love to point out that Krikalev holds another grimmer record. He was aboard Mir in 1991 when the Soviet Union collapsed beneath him. He launched as a Soviet cosmonaut and returned to a different country, the newly formed Russian Federation. His mission was extended because the political chaos on the ground made it difficult to organise a return flight. He spent 311 consecutive days in space on that mission, earning him the nickname the last Soviet citizen. So Krikalev didn't just time travel forward by milliseconds, he also orbited through one of history's most dramatic political transformations, watching his country dissolve from 400 kilometers up. That's a kind of time travel too, though not the kind Einstein predicted. Here's a quirky detail. NASA and Roscosmos actually monitor the cumulative time dilation for astronauts and cosmonauts, though it's more of an interesting footnote than a practical concern. The effects are far too small to impact human health or aging in any noticeable way. You'd need to spend thousands of years in orbit at ISS velocities to age even 1 second less than ground-based humans, and by that point, radiation exposure, bone density loss, and muscle atrophy would have killed you many times over. Time dilation is the least of an astronaut's worries, but the agency's calculated anyway because, well, it's cool, and it's a neat demonstration of relativity's reach. Every astronaut's mission patch could technically include a footnote. Time travelled 0.0xx seconds. The emotional weight of even tiny amounts of time travel is mostly conceptual, but it's worth sitting with. Imagine coming back from a year-long ISS mission and learning that technically you're now 0.01 seconds younger than you would have been if you'd stayed on Earth. It's meaningless in practical terms. You can't feel it, it doesn't show on your face, it doesn't extend your lifespan in any perceptible way. But philosophically, you've done something extraordinary. You've bent time. You've lived through slightly less temporal passage than everyone else. You're a proof of concept. You're evidence that the universe permits forward time travel, even if only in homeopathic doses. Now scale this up in your imagination. Imagine a spacecraft capable of travelling at 0.9 c, 90% the speed of light. A round trip to a star 10 light-years away would take about 22 years from Earth's perspective, but only about 10 years from the crew's perspective. They'd age 12 years less than Earth. That's not milliseconds. That's a decade of life skipped. That's your daughter graduating college while you're still experiencing the outbound leg of the journey. That's the same physics that gives Krikalev his 20 milliseconds, just applied at speeds we don't yet have the propulsion to achieve. The ISS is proof of principle. The terrifying part is that the principle works. The universe is ready for us to time travel dramatically. We just need to build the engines. If human-scale time travel feels too abstract, let's zoom into the subatomic level, where particles routinely time travel in ways we can measure with almost casual precision. Enter the muon, a subatomic particle that's essentially a heavier cousin of the electron. Muons are unstable. They exist for an average of just 2.2 microseconds before decaying into other particles. That's their half-life when measured in a lab at rest. But when cosmic rays, high-energy protons from deep space, slam into the upper atmosphere, they create showers of muons travelling at roughly 98% the speed of light. These muons are born about 10 to 15 kilometres above sea level, and according to their 2.2 microsecond lifespan, they should travel only about 660 metres before decaying. Basic math says they should never reach the ground. Yet we detect thousands of muons every second at sea level. They survive a journey they shouldn't be able to complete because, from our reference frame, time dilation stretches their lifespans. At 98% light speed, the Lorentz factor gamma is about 5. That means time flows 5 times slower for the muons relative to us. From our perspective, the muons live about 11 microseconds instead of 2.2 microseconds, more than enough time to traverse the 10 kilometres from their birthplace in the upper atmosphere to detectors on the ground. But here's the beautiful symmetry of relativity. From the muons' perspective, they're living exactly 2.2 microseconds. They don't experience time dilation. Instead, they experience length contraction. The atmosphere is squished down to only about 2 kilometres thick in their reference frame. Both perspectives are self-consistent. Both are equally valid. The muons reach the ground because relativity warps both time and space to make it possible. This isn't speculation. It's been experimentally verified over and over starting in the 1940s. Physicists like Bruno Rossi and David Hall measured the flux of muons at different altitudes, mountaintops versus sea level, and confirmed that more muons reach the ground than classical physics allowed. The discrepancy matched Einstein's predictions perfectly. Later experiments in particle accelerators created muons artificially and clocked their lifespans at various velocities. At rest, they decayed in 2.2 microseconds. Accelerated to near-light speed, their lifespans stretched exactly as the Lorentz factor predicted. Muons are tiny, short-lived, oblivious to their own fame, but they're incontrovertible evidence that velocity dilates time for objects travelling at relativistic speeds. Historians often note that the muon experiments were psychologically crucial for physicists in the mid-20th century, because they involved naturally occurring particles, not artificial setups. You didn't need a billion-dollar lab. You just needed a mountain, a detector, and patience. Some textbooks claim that muon observations were the first everyday confirmation of special relativity, accessible to university students with modest equipment. Others argue that the 1971 Hafele-Keating atomic clock flights were more publicly comprehensible because they involved macroscopic objects and commercial airplanes. Historians still argue whether particle evidence or human-scale evidence provided the more compelling narrative for popularizing relativity, though the physics community accepted both without reservation decades ago. Here's a quirky detail. Cosmic ray muons are one reason why you're slightly radioactive. Muons pass through your body constantly, about 1 per second through your hand, hundreds per second through your whole body. Most pass harmlessly through, but occasionally one collides with an atom, producing a tiny burst of ionizing radiation. It's not dangerous. You're exposed to far more radiation from naturally occurring potassium-40 in bananas or radon gas in basements, but it's happening all the time. You're being bombarded by time-traveling particles from space, and you never notice. The universe is deeply weird when you pay attention. Particle accelerators like the Large Hadron Collider take this to extremes. Protons in the LHC are accelerated to 99.9999991% the speed of light, which corresponds to a Lorentz factor of about 7,460. That means time flows 7,460 times slower for those protons relative to the lab frame. From the LHC's perspective, the protons circle the 27-kilometre ring about 11,000 times per second and survive for hours. From the proton's perspective, If we anthropomorphize ridiculously, they exist for just fractions of a second. But the LHC ring is length contracted to just 3.6 meters around. Both perspectives are consistent. Both are real. The protons are, in a very literal sense, time travelers from our future, experiencing hours of our time in their subjective milliseconds. Scientists exploit this constantly in experiments. Particles that would normally decay too quickly to study can be accelerated to near light speed, stretching their lifespans long enough to observe and measure. The Higgs boson, discovered in 2012, exists for about 10 to the power of minus 22 seconds before decaying, far too brief to detect directly. But the particles it decays into can be tracked, and because those secondary particles are often moving at relativistic speeds, their dilated lifespans give physicists enough time to reconstruct what happened. Time dilation isn't just a curiosity in particle physics, it's an essential tool. Without it, half the standard model would be invisible to us. The philosophical takeaway is this: relativity isn't restricted to exotic scenarios. It's woven into the fabric of reality at every scale. Muons prove it. GPS satellites prove it. Astronauts prove it. Atomic clocks prove it. You can measure time dilation with particles, with people, with devices in your pocket. The universe is utterly consistent. Velocity and gravity warp time, always, everywhere, without exception. Einstein's equations aren't approximations or idealizations. They're descriptions of how space-time actually behaves, confirmed in laboratories and in the atmosphere and in orbit and in the vacuum of particle colliders. The evidence is overwhelming, redundant, irrefutable. Time dilation is as real as friction, as gravity, as the fact that you need oxygen to breathe. It's just less obvious because you're not a muon hurtling through the atmosphere at 98% light speed. But give it time, maybe someday you will be. Now let's venture into the nightmare extreme of gravitational time dilation. Black holes, the universe's ultimate time thieves. If you thought neutron stars were intense, black holes are in a category so extreme they almost feel like science fiction. Except they're not. They're real, we've observed them, and we've even photographed one. A black hole is what you get when enough mass collapses into a small enough volume that space-time curves so severely that nothing, not even light, can escape. The boundary past which escape becomes impossible is called the event horizon, and it's the point of no return. Cross it, and you're doomed to fall forever into the singularity at the centre. But before you even reach the horizon, time dilation becomes so extreme that from an outside observer's perspective, you appear to freeze in time, hovering at the edge, your image redshifted and dimmed until you fade from view. You, meanwhile, experience no such pause. You fall inward in finite time, oblivious to the fact that the universe outside is aging into oblivion while you plunge toward destruction. Let's make this concrete. Suppose you're approaching Gargantua, the fictional supermassive black hole from the movie Interstellar. The film actually got the physics surprisingly right, consulting physicist Kip Thorne to ensure the time dilation effects were accurate. Near Gargantua's event horizon, space-time is so warped that 1 hour on a planet orbiting close to the black hole equals about 7 years far away from it. That's not Hollywood exaggeration. That's what general relativity predicts for a rapidly spinning black hole of Gargantua's mass. If you descended to that planet, spent a few hours exploring, then returned to your ship parked farther out, you'd find that decades had passed for your crewmates. Your children would be elderly, your mission would be ancient history, and you'd have aged a day, maybe 2. The math behind this involves the Schwarzschild metric for non-rotating black holes and the Kerr metric for rotating ones. Both describe how space-time curves near massive compact objects. The key quantity is the gravitational time dilation factor, which depends on how close you are to the event horizon. For a non-rotating black hole, the time dilation factor at distance r from the centre is roughly square root of 1 minus 2 gm over rc squared, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. As r approaches the Schwarzschild radius, the event horizon, that square root approaches 0, meaning time dilation approaches infinity. At the horizon itself, time effectively stops from an outside perspective. A clock falling into the black hole would appear to tick slower and slower, asymptotically approaching a freeze, though the clock itself, and anyone holding it, would sail past the horizon in finite proper time, unaware of the infinite time passing outside. Historians love to point out that Carl Schwarzschild derived his solution to Einstein's field equations in 1916, just 1 year after General Relativity was published, while serving in the German army during World War I. He was stationed on the Russian front suffering from a painful autoimmune disease and somehow still managed to solve one of the most important equations in astrophysics. He sent his solution to Einstein, who was both impressed and disturbed. The mathematics predicted objects so dense that not even light could escape, which seemed physically absurd at the time. Schwarzschild died just a few months later at age 42, never knowing that his Schwarzschild radius would become synonymous with black holes. Some scholars argue that Schwarzschild didn't fully grasp the implications of his own solution, while others credit him with predicting black holes decades before they were observationally confirmed. Historians still argue whether Schwarzschild deserves more recognition in popular science narratives, or whether his early death simply robbed him of the chance to develop his ideas further. Here's a quirky tidbit. The term black hole wasn't coined until 1967 by physicist John Wheeler. Before that, they were called frozen stars, or collapsed stars, reflecting the time dilation effect. An observer watching matter fall into one would see it appear to freeze at the horizon. Wheeler apparently hated the term frozen star because it was clunky and didn't capture the object's true nature. He started using black hole casually in lectures, and it stuck, despite some colleagues objecting that it sounded too much like slang. Now it's the universal term, immortalized in everything from textbooks to Star Trek episodes. Sometimes branding matters. The practical upshot of black hole time dilation is terrifying if you're trying to use one as a time machine. In principle, you could park a spacecraft near the event horizon of a supermassive black hole, wait a few hours, then fly back out to find that millennia had passed in the wider universe. You'd have time travelled forward dramatically. The catch? You'd need an enormous amount of energy to maintain your position near the horizon without falling in. Gravity would be trying to drag you down with a force of many Gs, so your engines would have to constantly fight it. You'd also be bathed in lethal radiation from the accretion disk, the superheated matter swirling into the black hole, glowing at millions of degrees. And if you miscalculated your position even slightly, you'd cross the horizon and be lost forever, crushed into the singularity. It's theoretically possible, but practically suicidal. Even if you survived, the psychological toll would be staggering. Imagine spending one subjective week near a black hole and returning to discover that 10,000 years have passed outside. Everyone you knew is dead. Your civilization might be extinct. Languages have evolved into unrecognizability. The Earth itself might be uninhabitable, the sun perhaps approaching its red giant phase. You'd be the ultimate time refugee, stranded in a future so distant you might as well be an alien. And there's no going back. Time only flows in one direction. The universe doesn't run in reverse. You skipped forward through the ages, and those ages are gone forever. That's the raw existential horror of black hole time dilation. It works exactly as the equations predict, and the equations don't care about your regrets. And yet, black holes exist. We've photographed the supermassive one at the centre of the galaxy M87, a blob of glowing accretion disks surrounding a shadow where the event horizon resides. We've detected gravitational waves from black hole mergers, ripples in space-time caused when two of these monsters spiral together and collide. We know they're out there, scattered throughout the universe, patient and indifferent, warping time so severely that hours become years, become centuries. They're not hypothetical, they're real, and if you got close enough, they'd steal your future. So let's talk about building an actual human-scale time machine. Not a thought experiment, not a particle in a collider, but a spacecraft designed to send a person forward through time in a meaningful way. You want to age 10 years while Earth ages 100. You want to visit the future, see what humanity becomes, maybe escape a war or a plague or a bad breakup. The good news, physics allows this. The bad news, the engineering is so absurdly difficult that it makes landing on Mars look like a trip to the grocery store. Let's walk through the requirements, the obstacles, and the nightmarish energy budgets that stand between you and your one-way ticket to the 23rd century. First, the goal. To experience significant time dilation, you need to travel at a substantial fraction of the speed of light, say 90% or higher. At 90% light speed, 0.9 c, the Lorentz factor is about 2.29, meaning you age about 44% as fast as someone stationary. 1 year for you equals 2.29 years for Earth. At 99% light speed, gamma is about 7.1. 1 year for you equals 7.1 years for Earth. At 99.9% light speed, gamma is 22.4. That's where things get dramatic. Travel for 5 years at 99.9 cents, and 112 years pass on Earth. You come back to a world where everyone you knew is dead, assuming anyone remembers you at all. That's the level of time dilation you'd need to make time travel subjectively interesting. Now, how do you get a spacecraft up to 99.9% light speed? You need propulsion, and not the chemical rockets we use today. Chemical rockets are pathetically slow by relativistic standards. The Saturn V, which sent astronauts to the Moon, reached about 11 kilometers per second, roughly 0.000037% the speed of light. To reach 0.9 c, you need to go 24,000 times faster. That requires either an unimaginable amount of fuel or a radically different propulsion mechanism. Let's consider a few options. Option 1, nuclear pulse propulsion, like the old Project Orion concept from the 1950s. You detonate nuclear bombs behind your spacecraft, surfing the shock waves to accelerate. It's insane, violent, and theoretically possible. Physicist Freeman Dyson calculated that an Orion-style ship could, in principle, reach about 3 to 5% the speed of light with a reasonable fuel supply. That's not enough for dramatic time dilation, but it's a start. To reach 90% light speed, you'd need thousands of bombs, each more powerful than those dropped on Hiroshima, and a spacecraft massive enough to withstand the repeated nuclear blasts without vaporizing. The fuel mass alone would dwarf the payload. And good luck getting international approval to launch a ship carrying a stockpile of thermonuclear weapons. Option 2, antimatter rockets. When matter and antimatter collide, they annihilate, converting 100% of their mass into energy via E equals mc squared. That's the most efficient fuel possible. A kilogram of matter meeting a kilogram of antimatter releases about 1.8 times 10 to the power of 17 joules, roughly 43 megatons of TNT equivalent. Channel that energy efficiently, and you could, in theory, accelerate a spacecraft to relativistic speeds. The problems? We've only ever created a few nanograms of antimatter in particle accelerators, and it costs roughly $62 trillion per gram. Storing antimatter is also nightmarishly difficult. It annihilates instantly on contact with matter, so you need magnetic containment fields that never ever fail, or your fuel tank becomes a gigaton explosion. Antimatter propulsion is theoretically perfect and practically impossible with current technology. Option 3. Laser sails. Mount a giant reflective sail on your spacecraft, then blast it with an enormously powerful ground-based laser array. The photons transfer momentum to the sail, accelerating the ship. Breakthrough Starshot, a real initiative funded by billionaire Yuri Milner, proposes using this method to send tiny probes, maybe a gram in mass, to Alpha Centauri at 20% light speed. Scale that up to a crude vessel, though, and you need a laser array with power outputs rivaling a nation's entire electrical grid, focused with perfect precision across billions of kilometers. And there's no way to slow down at the destination unless you build another laser array there, which you can't because you're arriving first. Laser sails are feasible for tiny probes maybe, but not for human-scale time machines. The energy requirements are almost offensively large. To accelerate a 1,000 kilogram spacecraft, very small by today's standards, to 90% light speed, you need about 4 times 10 to the power of 19 joules. That's roughly the total energy output of the United States for an entire year, focused into one ship. To reach 99% light speed, you need about 10 to the 20 joules. For 99.9% light speed, the energy requirements explode further, and that's just to accelerate. If you want to decelerate at the destination, which you probably do, unless splattering into a star system at near light speed counts as a successful mission, you need twice as much energy. You're now talking about energy budgets that dwarf the annual output of human civilization. Historians often point out that early spaceflight pioneers faced similar skepticism. In the 1920s, rocket scientist Robert Goddard was mocked by the New York Times for suggesting rockets could work in the vacuum of space. The Times issued a correction in 1969, the day after Apollo 11 landed on the Moon, admitting they were wrong. Some argue that dismissing relativistic spaceflight as impossible is just as short-sighted. Who knows what breakthroughs the next century might bring? Others counter that there are hard physical limits involving energy and mass that no amount of cleverness can bypass. Historians still argue whether human relativistic spaceflight is a matter of when or never, though most physicists lean toward never without a radical leap in energy technology. Here's a quirky detail. In the 1960s, physicist Robert Bussard proposed the Bussard ramjet, a spacecraft that scoops up interstellar hydrogen as it flies, fuses it for fuel, and uses the energy to accelerate further. In theory, it could reach relativistic speeds without carrying fuel. In practice, the hydrogen density in interstellar space is so low, about 1 atom per cubic centimetre, that your scoop would need to be hundreds of kilometres wide to collect meaningful amounts, and the drag from scooping would probably slow you down more than the fusion thrust accelerates you. The ramjet remains a beautiful idea that doesn't survive contact with reality. The bottom line, building a human-scale time machine is permitted by physics but staggeringly difficult by engineering. You need either impossibly efficient propulsion, impossibly large energy reserves, or impossibly light spacecraft. Or you wait a few centuries for technology to catch up, assuming civilization survives that long. The universe says, sure, you can time travel forward, just move really fast. And then it adds, under its breath, good luck with that. Let's talk about the cosmic speed limit, because even if you solve the engineering challenges, somehow you've built an antimatter reactor, harvested enough fuel, and constructed a ship that won't disintegrate, you still slam face first into the universe's most fundamental constraint. Nothing with mass can reach the speed of light. Not, it's really hard. Not, we haven't figured it out yet. It's impossible, prohibited by the structure of space-time itself. As you accelerate closer and closer to light speed, the energy required to go even fractionally faster increases exponentially, asymptotically approaching infinity. You could harness the entire energy output of every star in the observable universe, and you still couldn't push a single atom to exactly light speed. The universe has a speed limit, and it enforces it with mathematical brutality. Here's why. Einstein's special relativity reveals that as your velocity increases, three things happen simultaneously. First, your mass, or more precisely your relativistic mass, increases. The faster you go, the more massive you effectively become from the perspective of a stationary observer. Second, distances in your direction of travel contract due to length contraction. And third, time dilates, as we've discussed. These effects are linked through the Lorentz factor, gamma, which equals 1 over the square root of 1 minus v squared over c squared. At low speeds, gamma is nearly 1, and everything behaves normally. But as v approaches c, the denominator approaches 0, and gamma shoots toward infinity. That means your effective mass approaches infinity, requiring infinite energy to accelerate further. The universe simply won't let you cross that threshold. Let's put numbers to it. Accelerating 1 kilogram of matter from rest to 50% light speed requires about 1.5 times 10 to the 16th power joules, roughly the energy of a small nuclear bomb. Getting that same kilogram from 50% to 90% light speed requires about 1.1 times 10 to the power of 18 joules, the energy of a large thermonuclear warhead. From 90% to 99% light speed, about 9 times 10 to the power of 18 joules, several times the yield of the largest bomb ever detonated. From 99% to 99.9%, you're now at 10 to the power of 19 joules, approaching the total annual energy consumption of a developed nation. From 99.9% to 99.99%, the energy requirements double, and they keep doubling steeper and steeper every time you add another 9 to your percentage. By the time you reach 99.9999999% light speed, you need more energy than exists in entire star systems. The final approach to 100% requires literally infinite energy. The universe has drawn a line, and that line is the speed of light. Historians love to point out that Einstein himself found this result deeply unsettling when he first derived it. In his early papers, he worried the infinite energy requirement might indicate a flaw in his equations, but experimental evidence kept confirming the predictions. Particle accelerators push electrons, protons, and other particles to 99.9999% light speed and beyond, and the energy-velocity relationship matches Einstein's equations perfectly. The Large Hadron Collider accelerates protons to 99.9999991% light speed, and it takes 13 trillion electron volts to get them there. Absurd energies for something as small as a proton. Some physicists in the early 20th century speculated that maybe there was a loophole, a way to sidestep the mass-energy relationship. But a century of experiments has found none. Historians still argue whether the cosmic speed limit represents a fundamental feature of reality, or merely a limitation of our current understanding, though the consensus overwhelmingly favours the former. Here's a quirky detail. Photons themselves, particles of light, travel at exactly the speed of light because they have zero rest mass. For massless particles, the equations of relativity don't blow up. They move at c always, in every reference frame, no matter what. From a photon's perspective, a phrase physicists hate because photons don't have reference frames in the usual sense. The journey from the Sun to Earth takes 0 time. 8 minutes in our frame, 0 in the photons. The photon is emitted and absorbed in the same instant from its own experience. It's timeless, ageless, untouched by the passage of time. Giving a particle even the tiniest amount of mass, though, dooms it to speeds below light speed forever. Mass is the anchor that chains you to sublight existence. You're made of mass. You're stuck. The practical implication is that even if you had a magical engine capable of providing limitless thrust, you'd never reach light speed. You'd keep accelerating, inching closer, 99%, 99.9%, 99.99%, but never quite arriving. Your clock would slow towards stopping, distances would contract towards zero, and your ship's energy would soar toward infinity. From Earth's perspective, you'd appear to asymptotically approach light speed, your image redshifted and dimmed, but you'd never cross that final threshold. And from your perspective, you'd feel constant acceleration, but you'd never subjectively experience travelling at light speed itself. You'd approach, forever, like Zeno's paradox made real. Some sci-fi stories try to cheat this limit with concepts like warp drives or hyperspace, which don't actually accelerate you to light speed, but instead manipulate space-time to bring your destination closer. The Alcubierre drive, proposed in 1994 by physicist Miguel Alcubierre, is a mathematical solution to Einstein's equations that describes a space-time bubble contracting space in front of a ship and expanding it behind, allowing the ship to effectively travel faster than light relative to distant observers without locally exceeding light speed. It's ingenious, elegant, and requires exotic matter with negative mass-energy density, something we've never observed and have no idea how to create. Most physicists consider the Alcubierre drive a fascinating mathematical curiosity, not a blueprint for actual propulsion. It's technically allowed by the equations, but so are perpetual motion machines if you ignore friction. Theory and practice are different countries, and the border crossing is heavily guarded. The emotional weight of the cosmic speed limit is profound. It means the universe is fundamentally isolating. Even if we had the energy to send ships at 99.9% light speed, interstellar travel would still take years, decades, centuries. The nearest star system, Alpha Centauri, is 4.37 light-years away. At 99.9% light speed, the trip takes about 4.4 years from Earth's perspective, and about 6 months from the crew's perspective. Not terrible, but still a one-way journey into the future. The Andromeda Galaxy, 2.5 million light-years away, would take 2.5 million years from Earth's perspective, even if you travelled at 99.99999% light speed, though the crew might experience just years due to extreme time dilation. But Earth would be unrecognisable when they returned, if it existed at all. The speed limit doesn't just make interstellar travel hard, it makes the universe lonely. We're trapped in our little bubble of causality, unable to reach most of the cosmos within any human meaningful time frame. The stars we see are echoes from the past, light that left centuries or millennia ago. We're ghosts to each other, separated by distances so vast that even moving at nearly the speed of light barely dents them. And the universe doesn't apologise. The cosmic speed limit isn't a bug in the code. It's a feature, possibly a necessary one. Some physicists speculate that if faster-than-light travel were possible, it would allow causality violations, effects preceding causes, time travel paradoxes, logical inconsistencies that might unravel the universe's coherence. The speed limit protects causality, ensuring the future can't send messages to the past, that causes always precede effects, that the timeline flows in one direction only. It's a prison, sure, but maybe it's the kind of prison that prevents chaos. You can time travel forward by moving fast, but you can never go home. The cosmic speed limit ensures it. Now let's confront the biological consequences of time dilation, because even if you somehow overcome the energy barriers and build a ship capable of near-light speeds, you still have to reckon with what happens to your actual body when time flows differently for you than for the rest of the universe. The physics is clear, you'll age slower relative to Earth, but your biology doesn't know that. Your cells, your DNA, your brain, they're all evolved to operate on a consistent timeline, synced with circadian rhythms and environmental cues. What happens when you tear yourself out of that context and fling yourself into a relativistic reference frame where hours become years outside your ship? The honest answer is, we don't fully know, because no human has ever experienced significant time dilation. But we can make some educated guesses, and some of them are unsettling. First, the good news. From your subjective perspective, nothing changes. Your heartbeat remains steady at 60-something beats per minute. Your cells divide at their normal rates, your neurons fire, your stomach digests, your immune system patrols for threats, all exactly as they would if you were sitting still on Earth. Special relativity is perfectly clear about this. All inertial reference frames are equivalent. If you're moving at constant velocity, you don't feel motion. You don't feel time dilation. You're in your own bubble of normal time, and everything inside that bubble behaves normally. If you're travelling at 99% light speed for what feels like 1 year to you, you'll age 1 year. You won't suddenly sprout grey hairs or find your muscles atrophied. Biologically, you're fine inside your reference frame. The problem arises when you interact with the outside universe, especially if you're accelerating or decelerating. Acceleration is not an inertial frame, you feel it. Your body experiences g-forces, which can be brutal. To reach 90% light speed in a reasonable subjective time, say 1 year, you'd need to accelerate at about 0.9 g continuously for that entire year. That's uncomfortable, but survivable. Astronauts train for worse. But if you want to reach 99.9% light speed, the acceleration phase becomes proportionally longer or more intense. And when you arrive and want to slow down, you experience the same forces in reverse. Your cardiovascular system, your bones, your inner ear's vestibular system, all evolved under Earth's 1g gravity, might struggle with prolonged acceleration. Some researchers speculate that future time travel ships would need rotating sections to simulate gravity during cruising phases, and acceleration couches filled with gel or liquid to distribute g-forces evenly across the body. It's not insurmountable, but it's not trivial either. Then there's radiation. Space is awash with high-energy particles, cosmic rays, solar wind, gamma rays from distant cataclysms. At relativistic speeds, these particles hit your ship with even more energy due to your velocity. A proton that would normally pass through harmlessly becomes a relativistic bullet, slamming into your hull and potentially into you. The Earth's atmosphere and magnetic field shield us from most of this radiation, but in deep space, travelling at near light speed, you're exposed. Your ship would need heavy shielding, meters of water, lead, or some advanced material to absorb the barrage. Even with shielding, some radiation gets through. Prolonged exposure increases your cancer risk, damages DNA, potentially affects cognitive function. And here's the kicker. Because of time dilation, your subjective journey might be short, say 5 years, but Earth experiences decades or centuries. If you return, you've skipped forward, but your body has accumulated radiation exposure equivalent to those 5 years. Depending on the dose, that could mean elevated cancer risk for the rest of your life. You time-travelled forward, but the universe left scars. Historians often note that early space medicine researchers in the 1950s and 60s were wildly optimistic about human adaptability. Some predicted that astronauts could withstand 10 Gs or more for extended periods with the right training. Reality proved harsher. Even 3G sustained acceleration is exhausting. The human body is fragile. a collection of fluid-filled sacs and electrical signals that evolved in a very specific environment. Taking it elsewhere requires care. Some scholars argue that this fragility will forever limit human spaceflight to slow, cautious journeys, while others believe bioengineering, genetic modification, cybernetic enhancements could eventually make us resilient enough for relativistic travel. Historians still argue whether humanity's biological limitations are a temporary obstacle or a permanent ceiling, though most agree we're nowhere near testing the hypothesis. Here's a quirky detail. Your gut microbiome, the trillions of bacteria living in your digestive system, might not handle time dilation well. These microbes have their own life cycles, reproducing every 20 minutes or so. They're synced to your body's rhythms, your diet, your environment. Disrupt that, and you risk dysbiosis, an imbalanced microbiome that can cause digestive issues, weakened immunity, even mood disturbances. Some microbiologists speculate that prolonged space travel, especially at relativistic speeds with all the stress and radiation involved, could decimate beneficial gut bacteria, leaving you vulnerable to infections or chronic illness. NASA already monitors astronaut microbiomes on the ISS and finds significant shifts after just months in space. Now imagine years at near-light speed, isolated, bombarded with radiation, eating freeze-dried rations. Your gut bacteria might stage a revolt. You'd time travel into the future with irritable bowel syndrome. Relativity doesn't care about your digestion. Then there's the psychological toll, which might be the worst part. You're aging slowly, but everyone else is aging fast. If you embark on a 10-year round trip, your time, at 99% light speed, Earth experiences about 70 years. Your parents are dead. Your friends are elderly or gone. Your children, if you have them, are now older than you. The world has moved on. Technologies have advanced. Languages have drifted. Cultural references are alien. You return to a planet where you're a relic, a curiosity, someone who remembers a past that feels like ancient history to everyone else. Psychologists call this temporal displacement, and it's a theme in military psychology research. Soldiers returning from deployment sometimes feel out of sync with civilian life after just months away. Imagine that feeling magnified 1,000-fold. You didn't just miss a few months, you missed lifetimes. How do you process that? How do you grieve? There's no therapy manual for everyone I loved died of old age while I was gone for a decade. You're not just a time traveller, you're a temporal orphan, marooned in a future that doesn't remember you. Some futurists speculate that if relativistic travel ever becomes common, societies will develop new social structures to cope. Maybe time traveller communities, people who've all skipped forward together, forming their own subcultures. Maybe contracts and legal frameworks that account for temporal displacement. Your assets frozen in trust, accessible when you return, decades later. Maybe psychological preparation programs, helping crew members pre-grieve their losses, accept the irreversibility of their choice. Or maybe it's simpler. Maybe no one takes the trip unless they have nothing left to lose, unless the future is worth more than the present. You don't become a time traveller because you're running toward something. You become one because you're running away. The universe allows forward time travel, but it doesn't shield you from the consequences. You'll age slower, sure, but you'll still age. You'll still accumulate damage, still face the psychological weight of irrevocable separation. Time dilation isn't a fountain of youth. It's a mechanism for skipping forward, and everything you skip is gone forever. Your biology survives the trip. Whether your mind does is another question entirely. Let's do the math on the heartbreak, because interstellar travel isn't just a physics problem, it's an emotional catastrophe dressed up as an adventure. Imagine this. You're offered a once-in-a-lifetime opportunity to join a mission to Proxima Centauri, the nearest star system, about 4.24 light years away. The ship can reach 90% the speed of light. The journey there and back, with a brief stopover to explore the planets, will take about 10 years of your subjective time. You'll get to see another star up close, maybe walk on an alien world, become one of the first interstellar explorers in human history. It's the ultimate adventure, the kind of thing that gets you into history books, that justifies your entire existence. You say yes. You board the ship. You wave goodbye to your 5-year-old daughter, promising you'll be back before she knows it, and you will be back from your perspective. 10 years. She'll be 15 when you return. Manageable, right? Wrong. From Earth's perspective, at 90% light speed with a Lorentz factor of about 2.29, your 10-year journey takes almost 23 years. You step off the ship barely into middle age, and your daughter is 28 years old. She's an adult. She's lived an entire adolescence and young adulthood without you. She graduated high school, maybe went to college, maybe got married, maybe had a child of her own. You missed all of it. You weren't there for her first heartbreak, her first job, her wedding. You're a stranger to her now, someone she remembers as a parent from childhood, but who never participated in the person she became. She aged 23 years. You aged 10. The math is correct. The outcome is unbearable. Now scale that up. Suppose the mission isn't to Proxima Centauri, but to a star 50 light years away. You're travelling at 99.5% light speed, giving you a Lorentz factor of about 10. Your round trip, including exploration time, takes 12 years from your perspective. You think you'll come back to a world 15, maybe 20 years older. You can handle that. But Earth experiences 120 years. Everyone you knew is dead. Your daughter lived her entire life and died of old age. Your grandchildren, whom you never met, are now elderly. Your great-great-grandchildren are strangers. The house you left behind has been demolished and rebuilt twice. The political landscape is unrecognizable. The technology is alien. You return to a world where you're not just out of place, you're out of time. You're an archaeological artifact that inconveniently still breathes. Historians love to point out that science fiction has explored this tragedy repeatedly, but it never quite lands until you personalize it. Joe Haldeman's novel, The Forever War, published in 1974, follows soldiers fighting an interstellar war at relativistic speeds. They leave for a few years of combat, return to Earth for reassignment, and find that decades have passed. Their families are gone. Society has evolved beyond recognition. They're veterans of a war nobody remembers, obsolete warriors in a world that's moved on. Haldeman, a Vietnam War veteran, was writing about the alienation soldiers feel returning from deployment, magnified by time dilation into existential horror. Some critics argue the novel is one of the most emotionally accurate depictions of relativistic travel's human cost, while others counter that it focuses too much on the individual and not enough on the societal implications. Historians still argue whether fiction or non-fiction better conveys the emotional stakes of time travel, though anyone who's read The Forever War probably leans toward fiction. Here's a quirky detail. In 1985, physicist Frank Tipler proposed a theoretical construct called a Tipler cylinder, a massive, infinitely long cylinder spinning at near-light speed, which could theoretically create closed time-like curves allowing backward time travel. It's never been built, obviously. Infinitely long cylinders are hard to source, and most physicists consider it a mathematical curiosity rather than a practical proposal. But even if it worked, it wouldn't solve the emotional problem. Travelling backward in time introduces its own nightmares, paradoxes, causality violations, the risk of erasing your own existence. Forward time travel, at least, is paradox-free. You just have to live with the consequences. The tragedy isn't abstract. It's waiting for you every time you think about interstellar exploration. Every mission proposal, every propulsion concept, every attempt to reach the stars faster. It all leads back to the same inescapable conclusion. You can't have both. You can't explore distant worlds and return to the people you love unchanged. The universe won't let you. Time dilation is the price of velocity, and velocity is the price of distance. You want to see Proxima Centauri? You'll pay in years stolen from Earth. You want to visit Andromeda? You'll pay in millennia. The farther you go, the more you lose. It's not a bug. It's the fundamental structure of space-time, indifferent to your heartbreak. Some psychologists who study isolation and long-duration spaceflight speculate that future crews on relativistic missions would need to be selected not for bravery or skill, but for detachment. You'd want people with no close family ties, no deep friendships, no strong connections to the present. People who are already adrift, already lonely, for whom losing decades or centuries on Earth wouldn't feel like loss, because they had nothing to begin with. It's bleak, but it might be necessary. Sending a well-adjusted, socially connected person on a time-dilated mission would be psychological cruelty. They'd spend the entire journey knowing what they'd sacrificed, unable to change it, and they'd return shattered. Better to send someone who's already detached, who sees the mission as escape rather than sacrifice. You don't send the astronaut who wants to come home. You send the one who doesn't have a home to come back to. And here's the final cruelty. It's not symmetrical. Your daughter, aging 23 years while you aged 10, at least had a life. She grew up, had experiences, became someone. You, meanwhile, were isolated in a metal tube hurtling through the void. 10 years of your life reduced to waiting, maintenance routines, staring at distant stars that barely shift position. You didn't gain a decade of youth. You lost a decade of living, and when you return, you find that loss was for nothing, because the people you wanted to share your adventure with are gone. You time-travelled forward, but forward is just another word for alone. The math is simple, really. Distance divided by velocity equals time, modified by the Lorentz factor. Plug in the numbers, and out comes tragedy. 10 years for you, 30 for Earth. 5 years for you, 80 for Earth. 1 year for you, a century for Earth. The equations don't care. They just calculate, indifferent and precise, mapping out exactly how much you'll lose, and you can't cheat them. You can't negotiate. The universe has done the math, and the math says, if you want to touch the stars, you'll pay in goodbyes. Irreversible, uncountable goodbyes. That's the one trip that turns hours into years. That's time dilation's gift and curse, wrapped together, indistinguishable and inescapable. Now take a slow breath. Let that sink in. The cold, infinite distance between what relativity permits and what the heart can endure. The universe allows you to travel forward through time, but it offers no comfort for the journey, no promise that the future will be kind, no assurance that anyone will be waiting when you arrive. Just the math, clean and merciless, counting the years you'll steal from yourself and everyone you love. We've spent so much time calculating trajectories and time dilation factors that it's easy to forget the most terrifying aspect of forward time travel. It's a one-way ticket. You can skip ahead 5 years, 50 years, 500 years, but you can never, ever go back. There's no rewind button, no way to undo your choice, no miraculous loophole in the equations that lets you return to the moment you left. Once you accelerate to relativistic speeds, and the universe outside ages faster than you, that time is gone. Those years on Earth tick past, events unfold, people live and die, and you're not there. And when you finally decelerate and step out of your ship, you're emerging into a future that doesn't know you, doesn't remember you, and certainly didn't wait for you. You're not visiting the future, you're exiled to it, permanently, with no possibility of return. That's the dilemma, and it's one that every single proposal for interstellar travel has to confront. Are we willing to send people forward in time knowing they can never come home? Let's be precise about why backward time travel is so much harder than forward. Forward time travel is easy, conceptually at least, because it's just relativity in action. Move fast or sit deep in a gravity well, and time flows slower for you. You experience less time than the outside universe, and presto, you've travelled forward. No paradoxes, no violations of causality, no exotic physics required. Backward time travel, though, runs headfirst into causality problems. If you could travel to the past, you could theoretically alter events, creating paradoxes. The classic example is the grandfather paradox. You travel back in time and accidentally kill your grandfather before he meets your grandmother. Now you're never born. But if you're never born, you never travel back in time to kill him. So he lives. You're born, you travel back, and you kill him again. An infinite loop of logical contradiction. The universe, as far as we can tell, doesn't permit that kind of nonsense. General relativity does technically allow for solutions that include closed time-like curves, paths through space-time that loop back on themselves, allowing an object to return to its own past. Physicist Kurt Gödel found one such solution in 1949, describing a rotating universe where time travel to the past was possible. The problem: our universe doesn't rotate the way Gödel's model requires. Other solutions involve wormholes, shortcuts through space-time connecting distant points. But keeping a wormhole open and stable requires exotic matter with negative energy density, which we've never observed and have no idea how to create. Theoretical physicist Kip Thorne explored this in the 1980s, showing that if you had a wormhole and moved one end at relativistic speeds, time dilating it, while keeping the other stationary, you could create a time machine allowing travel to the past. Beautiful in theory, impossible in practice. Historians love to point out that time travel to the past has always been more popular in fiction than in physics, precisely because it's dramatic. H.G. Wells' The Time Machine, published in 1895, kicked off the genre, though Wells' machine was pure fantasy with no attempt at scientific justification. Later writers like Robert Heinlein explored the paradoxes more seriously, with stories like By His Bootstraps and All You Zombies, twisting causality into pretzels for entertainment. Some scholars argue that fiction has shaped public perception of time travel more than physics has, creating unrealistic expectations that scientists spend careers trying to correct. Others counter that fiction inspired generations of physicists to explore the boundaries of what's possible. Historians still argue whether pop culture helps or hinders scientific literacy on topics like relativity, though most agree it's a mixed blessing, entertaining but often misleading. Here's a quirky detail. In 1991, physicist David Deutsch proposed a resolution to the grandfather paradox using the many worlds interpretation of quantum mechanics. In this view, when you travel to the past and kill your grandfather, you're not altering your own past. You're creating a branching timeline, a parallel universe where he dies, and you're never born in that branch. Meanwhile, your original timeline remains unchanged. You still exist because you came from a different branch. It's logically consistent, doesn't violate causality, and conveniently requires the existence of infinite parallel universes constantly splitting off from every quantum event. Most physicists find it philosophically unsatisfying, even if it's mathematically defensible. You're not really travelling to your past, you're hopping to a parallel world that resembles your past. That's not time travel, that's dimension hopping with extra steps. The practical upshot is that backward time travel, if it's possible at all, requires physics so far beyond our current understanding that it might as well be magic. Exotic matter, Stable wormholes, Tipler cylinders, closed time-like curves near rotating black holes. All of these are either purely theoretical or require conditions we can't create. Forward time travel, meanwhile, just requires velocity and patience. We know how to do it. We've measured it. We just haven't built the engines yet. That asymmetry is brutal. The universe lets you skip to the future easily, but guards the past jealously. Maybe because causality is fragile and the past can't be changed without unraveling reality's logical consistency. So you're stuck with the one-way ticket. You board your relativistic spacecraft knowing, absolutely, certainly knowing, that you will never return to the world you're leaving. Your friends will age and die. Your favourite places will be demolished or transformed. The music you love will become classic oldies, then ancient history. The political issues you cared about will be resolved or forgotten. You'll return to a world where you're an anachronism, a person out of context, carrying memories of a time that feels like mythology to everyone else, and there's no undo button, no time machine to take you back to the moment you left. You can only move forward, always forward, deeper into a future that grows stranger and more alienating with every passing year. Some philosophers argue this makes relativistic travel ethically questionable. Should we send people on missions knowing they'll be temporarily displaced? Is it informed consent if they can't truly grasp the emotional weight of losing decades or centuries until they've already experienced it? Others counter that humanity has always sent explorers into the unknown, knowing they might not return. Magellan's crew, Antarctic expeditions, astronauts on the moon. Risk is part of exploration. The fact that the risk is temporal rather than physical doesn't make it fundamentally different. You're sacrificing connection for discovery, and that's a trade humans have made since the first person climbed a mountain to see what was on the other side. But here's the difference. Those explorers could imagine returning, could hope for reunion. The relativistic traveller knows with mathematical certainty that return is impossible, not to the place they left anyway. They can physically come back to Earth, sure, but not to the Earth they departed from. That Earth is gone, aged into something else, and no amount of hoping or clever engineering will resurrect it. You're not just leaving on a journey. You're stepping into a river of time and letting the current carry you downstream while everyone you love stands on the bank, aging, waving, eventually disappearing from view. And the river only flows one direction. The universe is indifferent to this tragedy. It simply is. Space-time curving and stretching according to Einstein's equations, time dilating for fast-moving objects whether they want it to or not. There's no malice. No intention, no cosmic plan that says you must suffer this particular form of loss. It's just geometry. Space-time has a shape, and that shape has consequences, and one of those consequences is that you can't have both velocity and temporal connection. You choose one or the other, and the universe enforces your choice with absolute mathematical rigor. That's the one-way ticket dilemma. That's the price of touching the stars. Science fiction has been wrestling with time dilation's emotional devastation for decades, and some of the genre's most haunting stories aren't about aliens or explosions. They're about what it means to lose time, to be severed from your own era, to become a ghost in your own life. Let's walk through a few of the most psychologically brutal examples, because sometimes fiction captures truth better than textbooks ever could. These aren't just entertaining stories. They're thought experiments in grief, explorations of what happens when relativity's cold equations collide with the warm, messy reality of human relationships. And they're disturbingly plausible, because the physics behind them is sound. Every tragedy described in these stories could actually happen, is permitted by the universe, and might someday happen to real people if we ever build the ships. Start with Planet of the Apes, the 1968 film based on Pierre Boulle's novel. Astronaut Taylor and his crew travel through space in suspended animation, expecting to return to Earth after a relatively short subjective journey. But when they crash land on what appears to be an alien planet ruled by intelligent apes, they eventually discover the horrifying truth. They're on Earth, roughly 2,000 years in their future. Relativistic time dilation during their journey meant that while they aged minimally, Earth aged millennia. Human civilization rose, fell, was replaced by another species, and the planet they left behind is utterly gone. The final scene, Taylor collapsing in despair before the ruined Statue of Liberty, half buried in sand, is cinema's most iconic depiction of temporal displacement. He didn't travel to another world. He travelled too far forward in his own world, and there's no way back. The apes aren't the horror, time is the horror. Then there's Orson Scott Card's Ender's Game and its sequels, which explore time dilation more intimately. Young Ender Wiggin is recruited to command humanity's fleet in an interstellar war against an alien species. He's a tactical genius, but he's also a child, and the military exploits his youth and innocence. After the war, Ender travels the galaxy at relativistic speeds, aging slowly while centuries pass on Earth and its colonies. His older sister Valentine joins him, and together they become perpetual wanderers, the eternal teenagers who watch civilizations evolve and die while they remain biologically young. In Speaker for the Dead, set 3,000 years after Ender's Game but only decades later for Ender subjectively, he's a man haunted by guilt and disconnection. Everyone he knew is dust. He's functionally immortal through time dilation, but it's an accursed immortality. He can't die, but he can't live either, not really. He exists in the margins of history, forever alien to the present. Joe Haldeman's The Forever War mentioned earlier deserves deeper exploration because it's perhaps the most emotionally realistic depiction of relativistic warfare. Protagonist William Mandela is conscripted to fight an interstellar war against the Taurans, an alien species humanity barely understands. Each combat mission involves travelling light years at near-light speed, which means Mandela ages months while Earth ages years or decades. He fights a battle, returns to base for reassignment, and finds that society has transformed. Slang has changed. Political systems have shifted. His girlfriend, left behind on Earth, ages normally while he stays young. They try to reconnect between missions, but each reunion is more strained. She's 30, then 50, then dead of old age while he's still in his 20s. By the novel's end, Mandela has aged about 10 years, but over 1,000 years have passed on Earth. The war he's fighting was resolved centuries ago through diplomacy and mutual understanding, but because of light-speed communication delays, he didn't know. He's a soldier in a war that ended before he was born from his enemy's perspective. The novel is a brutal meditation on alienation, on the impossibility of returning home, on the way war and time steals your life even if you survive. Historians and critics often argue about whether these stories are cautionary tales or celebrations of human adaptability. Some scholars claim The Forever War is anti-war propaganda disguised as science fiction, a Vietnam War allegory condemning the futility of conflict. Others read it as tragedy, mourning the inevitable losses that come with progress and expansion. Ender's Game has been criticised and praised for its depiction of a child weaponised by adults, with some seeing it as a condemnation of militarism and others as a coming-of-age story about accepting responsibility. Planet of the Apes is variously interpreted as a warning about nuclear war, environmental collapse, or humanity's hubris. Historians still argue whether science fiction's value lies in its predictions or its metaphors, though most agree the best stories work on both levels simultaneously. Here's a quirky detail. Larry Niven's 1967 short story, Neutron Star, explores time dilation near a neutron star's immense gravitational field. The protagonist, Beowulf Schaefer, flies close to a neutron star in a supposedly indestructible spacecraft. The tidal forces, the difference in gravitational pull between his head and feet, nearly kill him, but the time dilation also means he experiences the approach differently than outside observers. Niven was one of the first sci-fi writers to rigorously apply real physics to his stories, consulting with physicists to get the details right. His work inspired a generation of hard science fiction authors who prioritized scientific accuracy, sometimes to the annoyance of readers who preferred fantasy. But that rigor made the emotional stakes hit harder. When the physics is plausible, the tragedy feels inevitable rather than contrived. The recurring theme in all these stories is isolation. Time dilation doesn't just move you through time, it severs you from everyone moving at a different rate. You become untethered, adrift, a temporal refugee. Your culture evaporates, your language evolves into something unrecognizable. The people you love vanish into the past, and you can't stop it. You can't slow down time for everyone else. You can't speed up your own clock to catch up. You're locked in your reference frame, watching the universe age around you, powerless to change it. The stories aren't about technology or aliens. They're about loneliness on a cosmological scale. The kind of loneliness that comes from realizing the universe doesn't care if you're connected to anyone or anything. It just ticks forward, indifferent. Some psychologists who study long-duration spaceflight recommend these stories as required reading for anyone considering interstellar missions, not to discourage them, but to prepare them. If you're going to experience even mild time dilation, you need to understand what you're signing up for. Fiction, weirdly, might be better preparation than technical briefings, because it engages the emotional reality, not just the numbers. Reading about William Mandela returning to an Earth 1,000 years older hits differently than hearing, "Your round trip will experience significant temporal displacement." The former makes you feel it. The latter is just jargon. And here's the uncomfortable truth. We don't know if humans can psychologically handle significant time dilation. We've never tested it. The longest anyone has stayed in space is about 437 consecutive days. Valery Polyakov on Mir, 1994 to 1995, and he experienced maybe a few milliseconds of time dilation. We have no data on what happens when someone ages 10 years while Earth ages 50, or 1 year while Earth ages a century. Will they adapt? Will they break? Will they find meaning in their displacement? Or will it destroy them? Science fiction offers guesses, some optimistic, most pessimistic. But the real answer is, we won't know until we try. And the first people to try will be guinea pigs, test subjects in an experiment with no control group, and no way to undo the results if it goes badly. The universe permits forward time travel, but the stories remind us that permission isn't the same as kindness. You can travel to the future, but the future doesn't promise you belonging, happiness, or reunion. It just promises that you'll arrive, older in body but disconnected in context, carrying memories of a world that no longer exists. That's what the fiction teaches us. That's the lesson buried in every story about relativistic journeys, every narrative about astronauts returning to find their loved ones gone. The stars are reachable, but reaching them costs more than fuel. It costs time, connection, and the irreplaceable pieces of your life that can never be reclaimed. The stories know this, the characters suffer it, and if we ever build the ships, the astronauts will live it. Now let's tackle the question that everyone asks eventually, the one that seems to undermine everything we've discussed. If forward time travel is easy, and backward time travel is hard, can we travel backward at all? Is there any loophole, any exotic scenario, any speculative physics that would let you return to the past, or at least to your own past reference frame, and undo the temporal displacement of a relativistic journey? The short answer is probably not. The long answer is maybe under circumstances so extreme and speculative that they make building a relativistic starship look trivial by comparison. Let's explore the possibilities, the paradoxes, and the reasons why the universe seems determined to protect the past from meddling time travelers. First, the paradoxes. We've mentioned the grandfather paradox, but it's worth spelling out why it's so troublesome. If you travel to the past and prevent your own birth, you create a logical contradiction. You exist because you just travelled backward, but you don't exist because you were never born. Some resolutions have been proposed, most famously the Novikov self-consistency principle, named after physicist Igor Novikov. This principle states that if time travel to the past is possible, the timeline must be self-consistent. Events must unfold in such a way that paradoxes are avoided. If you try to kill your grandfather, something will always prevent you. Your gun jams, you miss, you change your mind. Because the universe doesn't permit inconsistent timelines. You're free to act, but only in ways that are consistent with the history you came from. It's a deterministic view that eliminates free will for time travelers, which is philosophically unsatisfying but mathematically tidy. Another resolution is the many worlds interpretation we touched on earlier. When you travel to the past and alter events, you're not changing your past. You're creating a branching timeline, a parallel universe where the altered events occur. Your original timeline remains intact. This avoids paradoxes at the cost of requiring infinite parallel universes, which is conceptually extravagant. Physicist David Deutsch argues this is the only consistent way to allow backward time travel within quantum mechanics, though most physicists remain skeptical. The many worlds interpretation has other problems. It's experimentally untestable for one, but it does technically solve the paradox issue. You just have to accept that returning to your past means visiting a universe that resembles your past, which isn't quite the same thing. Now the mechanisms. General relativity does permit solutions that include closed time-like curves, paths through space-time that loop back on themselves. Kurt Gödel's rotating universe model is one example, but our universe doesn't rotate that way. Wormholes are another. A wormhole is essentially a tunnel through space-time, connecting two distant points. If you had a stable, traversable wormhole, big if, you could theoretically move one end at relativistic speeds, time dilating it, while keeping the other stationary. After enough time, the moving end would be younger than the stationary end. Enter the stationary end, and you'd emerge from the moving end at an earlier time, effectively travelling backward. Physicist Kip Thorne worked out the details in the 1980s, but there's a catch. Keeping a wormhole open and stable requires exotic matter with negative energy density, something we've never observed. The Casimir effect, a quantum phenomenon where two metal plates in a vacuum attract each other, produces a kind of negative energy, but on scales so tiny it's useless for engineering. Scaling it up to wormhole size is pure speculation. Then there are rotating black holes, described by the Kerr metric. A maximally rotating black hole has a ring singularity instead of a point singularity, and the space-time around it is so twisted that, in theory, closed time-like curves exist inside the event horizon. You could, hypothetically, orbit the singularity in a specific way and emerge at an earlier time. The problems? First, you'd have to cross the event horizon, which means you can't escape to report your success. Second, the interior of a rotating black hole is so chaotic and poorly understood that most physicists doubt closed time-like curves. They're actually traversable. You'd be torn apart by tidal forces or quantum instabilities. Third, even if it worked, you'd only travel back to a time after the black hole formed, not before. You can't use a black hole to visit the dinosaurs. It's useless for practical time travel. Historians often point out that time travel to the past has never had any experimental support, unlike time travel to the future, which is measured routinely. The closest we've come is thought experiments and mathematical models, none of which have been realised. Some argue this suggests backward time travel is fundamentally impossible, that the universe's structure prohibits it. Others counter that we simply haven't discovered the right physics yet, much like heavier-than-air flight seemed impossible before the Wright brothers, or nuclear energy before Einstein. Historians still argue whether backward time travel is a question of technology or ontology, though the consensus leans toward ontologically prohibited, meaning the universe's laws forbid it, not just our current capabilities. Here's a quirky detail. In 1974, physicist Frank Tipler proposed the Tipler cylinder, an infinitely long, extremely dense cylinder rotating at near-light speed. The rotating mass would drag space-time around it, creating closed time-like curves that would allow time travel to the past. The problems are obvious: infinite length, immense density, comparable to a neutron star, and relativistic rotation speeds. Building one would require rearranging the mass of entire star systems and engineering beyond any conceivable future technology. It's a mathematical curiosity, not a blueprint. Tipler himself later admitted it's probably impossible, but the solution remains in the physics literature as a reminder that general relativity permits some truly bizarre scenarios under extreme conditions. The emotional reality of backward time travel, if it were possible, is its own kind of horror. Suppose you could return to your past. You've aged 10 years travelling at relativistic speeds, and Earth has aged 50. You decide to use a wormhole or a Tipler cylinder or whatever exotic mechanism to go back to the moment you left. You step out, and your 5-year-old daughter is there, unchanged, greeting you as if you'd never left. But you have left. You've aged 10 years. You've seen things, experienced isolation, carried the weight of decades, and now you're supposed to pretend it didn't happen. The timeline is self-consistent, but you're not. You're carrying memories of a future that from this moment's perspective hasn't occurred yet. You're traumatized by events no one else remembers. You're a time traveler in your own life, forever out of sync. Is that better than never returning at all? It's not clear. The universe seems to guard the past jealously, and maybe that's for the best. Causality is fragile. Cause must precede effect, or logic breaks down. If the future could send messages to the past, if effects could precede causes, the universe would become a tangled mess of contradictions. The cosmic speed limit, the prohibition on faster-than-light travel, the lack of observed closed time-like curves, all of these might be mechanisms protecting causality from violations. Forward time travel is safe. It doesn't threaten logical consistency. You're just moving through time at a different rate, and causality remains intact. Backward time travel, though, opens the door to paradoxes, to timelines eating themselves, to the collapse of coherent history. The universe says no, and it enforces that no with the full weight of physical law. So can we travel backward? The honest answer is, almost certainly not, and if we could, we probably shouldn't. The physics is speculative, the engineering is impossible, and the paradoxes are nightmarish. Forward time travel is permitted, measurable, and waiting for us to build the engines. Backward time travel is a mathematical ghost, haunting the equations but never materializing in reality. You can skip to the future, but you can't go home. That's the universe's rule, and no amount of clever thinking has found a way around it. Time flows forward, always forward, and the past is sealed behind you, inaccessible, immutable, and forever out of reach. Let's confront the logical nightmare head-on, the grandfather paradox and its proposed solutions, because even if backward time travel is probably impossible, understanding why it's problematic illuminates something deep about causality, free will, and the structure of time itself. The grandfather paradox is simple to state. You build a time machine, travel to the past, and kill your grandfather before he has children. This prevents your parent from being born, which means you're never born, which means you never build a time machine or travel back to kill him. So he survives, has children, you're born, you travel back, and you kill him again. An infinite loop of contradiction. The paradox reveals that allowing unrestricted action in the past creates logical inconsistencies that seem to break the universe. So how do physicists propose resolving this? And do any of the solutions actually work? Or are they just elaborate ways of avoiding the conclusion that backward time travel is impossible? The first and most famous resolution is the Novikov self-consistency principle, formulated by Russian physicist Igor Novikov in the 1980s. Novikov's idea is straightforward. If time travel to the past is possible, then the universe enforces self-consistency. The timeline must form a closed, consistent loop with no contradictions. If you travel to the past intending to kill your grandfather, the universe will conspire to prevent you, not through active intervention, but through the inevitable unfolding of events. Your gun jams, you slip and miss, you have a change of heart at the last moment. Something always prevents the paradox because the universe doesn't permit inconsistent histories. You have agency, but only within the bounds of what's consistent with the timeline you came from. It's a bit like being in a play where you can improvise your lines, but the ending is already written. This resolution is philosophically troubling because it seems to eliminate free will for time travelers. If you can't kill your grandfather because the timeline forbids it, are you really free? Novikov would argue yes. You're free to try, and you're free to fail, and the reasons for your failure are physical, gun jams, slippery floor, rather than metaphysical. But critics point out that if your failure is inevitable, predetermined by the self-consistency requirement, then your actions aren't truly free. They're constrained by the need to preserve the timeline. It's determinism dressed up as choice. Some physicists find this acceptable, others find it deeply unsatisfying. The debate hinges on whether you think free will is compatible with determinism, a question that's plagued philosophy for millennia and isn't resolved just because you add time travel to the mix. The second major resolution is the many worlds interpretation, which we've touched on before. In this view, when you travel to the past and kill your grandfather, you don't alter your own past. You create a branching timeline, a parallel universe where he dies, and you're never born in that branch. Your original timeline remains unchanged. You still exist there because you came from a different branch. There's no paradox because you're not changing your past. You're hopping to a parallel world that happens to resemble your past up to the point of your arrival. From that point forward, the two timelines diverge. In one branch, your grandfather survives and you're born. In the other, he dies and you're not. Both timelines are equally real, existing simultaneously in the quantum multiverse. This resolution avoids paradoxes cleanly, but at the cost of ontological extravagance. You have to accept the existence of an infinite number of parallel universes constantly branching off from every quantum event. You also have to accept that returning to your past isn't really returning. It's just visiting a similar universe, and there's no way to test this experimentally, because by definition, you can't access other branches to verify they exist. The many worlds interpretation is mathematically consistent and philosophically popular in some circles, but it's also deeply speculative. It solves the grandfather paradox by redefining what past means, which some critics argue is cheating. A third, darker resolution, is the chronology protection conjecture, proposed by Stephen Hawking in 1992. Hawking suggested that the laws of physics might actively prevent time travel to the past by making it impossible to create closed time-like curves in the first place. Whenever you try to build a time machine, assembling a wormhole, spinning up a Tipler cylinder, whatever, quantum effects would intervene, creating a feedback loop of vacuum fluctuations that would destroy the mechanism before it becomes operational. The universe, in other words, protects its own chronology by ensuring that time machines self-destruct. Hawking called it keeping the universe safe for historians. It's a compelling idea, though it's more of a conjecture than a proven theorem. We don't have the physics to definitively say whether chronology protection is real, but the fact that we've never observed closed time-like curves or time travelers from the future is suggestive. Historians of science love to point out that Hawking's conjecture was partly tongue-in-cheek, a playful jab at physicists who took backward time travel too seriously. But it also reflects a genuine concern. If time travel to the past were possible, where are the time travelers? We should see evidence of them. Anachronistic technology, historical records of people appearing out of nowhere, lottery winners who seem suspiciously well-informed. The fact that we don't is called the Fermi paradox of time travel, and it suggests either that backward time travel is impossible, or that future civilizations choose not to visit the past, or that they're here but hiding effectively. Most physicists lean toward the first explanation. Historians still argue whether the absence of observed time travelers is strong evidence for impossibility, or just weak evidence for caution, though the lack of even a single confirmed case is telling. Here's a quirky detail. In 1991, physicist Kip Thorne and his student Michael Morris explored whether you could use a wormhole to send messages to your own past. Not a person, just information. They found that even this limited form of time travel runs into problems. If you send a message backward telling your past self not to send the message, you create a paradox. The Novikov self-consistency principle would require that something prevents the message from changing your decision. Maybe it arrives garbled, or you misunderstand it, or you ignore it. But if self-consistency is enforced, then the message's content is constrained. You can only send messages that are consistent with you having received them, which limits the information content severely. It's time travel, but it's almost useless because you can't change anything. The past is a read-only file. You can view it, but you can't edit it. The emotional stakes of these paradoxes are rarely discussed, but they're profound. Imagine successfully travelling to the past, intending to save a loved one from an accident, only to find that no matter what you do, they die anyway. You warn them, but they don't listen. You physically restrain them, but they slip away. The accident happens exactly as history recorded because self-consistency demands it. You're helpless, watching the tragedy unfold again, unable to change it despite all your knowledge and effort. That's the cruelty of the Novikov principle. The past is fixed not by decree, but by the logical structure of time itself. You can visit, but you can't alter. You're a ghost in your own history, present but powerless. Or imagine the many worlds alternative. You save your loved one, but only in a branching timeline. They survive and live a full life in that branch. But in your original timeline, the one you came from, they're still dead. You've created a universe where they live, but you can't go back to your original timeline to enjoy that outcome. You're stranded in a branch where you're a stranger, where everyone thinks you're insane for claiming to be from the future. Your loved one is saved, but not in any way that benefits you. You've traded your entire existence for the existence of an alternate universe version of someone you love. That's selfless, maybe, but it's also a form of suicide. You've erased your connection to your own past to create a better past for someone else. The universe's apparent prohibition on backward time travel might be a mercy. If you could change the past, you'd be haunted by every decision you didn't make, every tragedy you didn't prevent, every mistake you didn't correct. The past would become an infinite burden of could-have-beens. Forward time travel is clean. You skip ahead, you lose connection, but at least the past is settled. Backward time travel would unsettle everything, turning history into a negotiable draft rather than a fixed text. Maybe the universe protects the past not to torment us, but to free us from the impossible weight of infinite revision. You can't change what's behind you. You can only move forward. That's time's gift, disguised as a limitation. Now let's step away from the physics for a moment and consider the legal and ethical chaos that time travel would unleash on society. Forget the engineering challenges, the energy requirements, the paradoxes. Imagine that tomorrow, someone announces they've built a working relativistic spacecraft capable of sending people decades or centuries into the future. Congratulations, you can now time travel forward. But who gets to go? Who owns the property you left behind? Are you legally dead if you skip forward 100 years? Can you vote in elections for a future you won't experience? What happens to your debts, your contracts, your marriage? Time travel isn't just a physics problem, it's a legal nightmare, an ethical minefield, and a social experiment with no historical precedent. Let's walk through some of the questions that no law currently addresses because they've never needed to until now. Start with property. You own a house, you board a spacecraft, travel at 99% light speed for what feels like 5 years to you, and return to find that 50 years have passed on Earth. What happens to your house? In most legal systems, abandoned property eventually reverts to the state or can be claimed by others. But you didn't abandon it. You were just gone, travelling. Do you still own it? Some jurisdictions have laws for people declared legally dead after disappearance, but those assume you're actually dead, not time travelling. If you return, alive, 50 years later, do you have a claim? What if someone else has been living there for decades, paying taxes, maintaining it? Do they have squatters' rights? What if the city demolished your house and built a highway through the lot? Do you get compensation? And if so, at what value? 1970s prices or 2020s prices? There's no legal framework for this. Property law assumes time flows at the same rate for everyone. Time dilation breaks that assumption. Then there's inheritance. Suppose you have children. You leave on a 10-year mission, your time, but 30 years pass on Earth. Your children are now middle-aged. If you die during the mission, they inherit your estate, standard procedure. But what if you return alive when they're 50 years old? Are they still your dependents? Do you regain legal custody of your assets, or have they already been distributed? What if they've spent your money assuming you were never coming back? What if you return to find they've legally declared you dead, inherited everything, and resent your reappearance because it complicates their lives? Family law is built on assumptions of shared temporality. Time travel shatters that. You're a parent, but you're younger than your children. You're technically their elder by birth date, but they've lived longer. Who owes whom respect, care, legal responsibility? It's a mess. Marriage is even worse. You're married. You leave on a relativistic journey. Your spouse stays behind. From your perspective, you're gone 10 years. From your spouse's perspective, you're gone 50 years. Are you still married when you return? Most marriage vows say, till death do us part, but what about till time dilation does us part? Your spouse aged 50 years. They might have remarried, assuming you were gone forever. They might have grandchildren. They might be elderly or dead. If they remarried, are they a bigamist? If you remarry during your journey thinking they've moved on, are you a bigamist? What if you return and want to resume the marriage, but your spouse is now 80 years old and you're 35? The power dynamics, the physical reality, the emotional connection, everything is asymmetrical. Some ethicists argue that time-dilated journeys should automatically annul marriages unless both partners travel together, preserving temporal synchrony. Others say that's state overreach, infringing on personal relationships, There's no consensus because the scenario has never existed. Now consider debt. You take out a 30-year mortgage, then you board a spacecraft and time travel forward 50 years. When you return, is the debt paid off because 30 years have passed? Or do you still owe money? Because from your perspective, you've only been gone 5 years. What about interest? Does it accrue based on your subjective time or objective time? If you borrowed money at 5% interest for 30 years and 50 years pass, have you defaulted? If you return with no means to pay, can creditors seize your assets even though you weren't present to earn income? Some legal scholars propose that time-dilated travellers should have their debts frozen, paused during their journey, then resumed upon return. But that's wildly unfair to creditors, who could have loaned the money to someone else. Others suggest debt should be calculated in objective Earth time, making time travel financially ruinous for anyone with obligations. Either way, someone gets screwed. The law can't accommodate radically different temporal reference frames without creating injustice somewhere. Historians of law often note that every major technological shift, railroads, telephones, the internet, required new legal frameworks, often developed reactively after problems arose. Some argue that time travel law will follow the same pattern. Someone will take a relativistic journey, return to legal chaos, and courts will hash out precedents case by case. Others worry that without proactive legislation, early time travellers will be exploited or abandoned, their rights ignored because no law protects them. Historians still argue whether legal systems adapt fast enough to protect individuals during technological upheaval, with historical evidence suggesting they usually don't. Time travellers might become second-class citizens, legally adrift, until society catches up, if it ever does. Here's a quirky detail. In 2015, a legal theorist named Andrew Koppelman published a tongue-in-cheek paper exploring the citizenship status of time travellers. If you leave the United States in 2025 and return in 2125, are you still a US citizen? Most citizenship laws assume continuous presence, or at least existence, within a single temporal stream. If the country dissolved and reformed under a different government during your absence, do you have citizenship in the new nation, or are you stateless? Koppelman concluded that without specific legislation, time travellers could find themselves in legal limbo, possessing documents from a defunct nation and no clear path to citizenship in the present. It's absurd, but it's also plausible. Bureaucracies are not designed for time travel. Then there's the ethical question of who gets to go. Relativistic spacecraft, if they're ever built, will be phenomenally expensive, likely funded by governments or billionaires. Who decides who boards? Do you hold a lottery? Prioritize scientists and explorers? Sell tickets to the wealthy? Creating a new form of temporal inequality, where the rich can escape to the future while the poor are left behind. Some philosophers argue that time travel should be restricted to volunteers with no close family ties, minimizing the social disruption. Others say that's discriminatory, punishing people for being connected. And what about consent? If you're offered a berth on a relativistic mission, can you truly consent if you don't fully understand the emotional cost of temporal displacement? You might think you're ready, but how do you prepare for returning to a world where everyone you love is dead? Some ethicists propose mandatory psychological screening and a waiting period, like adopting a child or buying a gun. But even that assumes we know what traits predict successful adaptation, which we don't. There's also the question of representation. If you're going to be gone for 50 Earth years, should you still have a vote in elections? You won't experience the consequences of policies enacted during your absence, so should you have a say in them? Some political theorists argue that time travellers should forfeit voting rights during their journey, resuming them upon return. Others say that's disenfranchisement, stripping citizens of their rights for participating in exploration? There's no easy answer. Democracy assumes a shared temporal experience. We vote, we live with the consequences, we vote again. Time travel breaks that loop. You vote, you leave, you return to find the consequences have played out over decades without you. You're voting for a future you'll skip, which feels either irresponsible or meaningless, depending on your perspective. The universe permits forward time travel, but human society isn't equipped for it. Our laws, our institutions, our social contracts, all are built on the assumption that time flows uniformly for everyone. Break that assumption, and the entire structure wobbles. We'd need new legal categories: time-displaced persons, temporal trusts, relativistic marriage contracts, dilation-adjusted debt instruments. We'd need international treaties addressing citizenship and jurisdiction across temporal reference frames. We'd need ethical guidelines for who can travel, under what circumstances, with what protections. None of this exists. None of it is even being seriously discussed outside niche academic circles. The physics is ready, society is not. And if we ever build the ships without first building the legal and ethical frameworks, the first-time travellers will be pioneers in the worst sense, venturing into unknown territory with no map, no rights, and no guarantee that anyone will care about their fate when they return. Let's bring this forward into the nearish future and talk about the missions that are actually being proposed. Not hypothetical journeys to distant galaxies, but real projects with funding, timelines, and engineering teams trying to solve the relativistic travel problem right now. These aren't science fiction. They're on drawing boards, in budget proposals, and in some cases already in early testing phases. And while none of them will produce dramatic time dilation, not yet, they're the first steps toward a future where humans routinely experience measurable temporal displacement. The missions are modest by our earlier standards, but they're proof that humanity is inching slowly and expensively toward becoming a time-travelling species. Let's look at three of the most serious proposals and what they tell us about where we're headed. First, Breakthrough Starshot, announced in 2016 and backed by billionaire Yuri Milner, physicist Stephen Hawking, and Facebook's Mark Zuckerberg. The goal? Send a fleet of tiny spacecraft, each about the size of a postage stamp weighing maybe a gram, to Alpha Centauri, 4.37 light-years away, within a human lifetime. The propulsion method is a ground-based laser array, possibly located in the high deserts of Chile, that would blast the spacecraft's reflective sails with concentrated light, accelerating them to 20% the speed of light within minutes. At that velocity, the journey to Alpha Centauri takes about 20 years. The probes carry cameras, sensors, and communication equipment, and they transmit data back to Earth as they fly past any planets in the Alpha Centauri system. It's not a crewed mission. No human could survive the acceleration, but it's a proof of concept. If we can send gram-scale probes at 0.2 C, we've demonstrated relativistic spaceflight, even if the time dilation is modest. At 20% light speed, gamma is only about 1.02, meaning the probes experience about 2% less time than Earth observers. The challenges are immense. The laser array needs to output about 100 gigawatts, roughly the power of 100 nuclear reactors, focused with insane precision across billions of kilometers. The sails need to be incredibly lightweight and reflective, surviving temperatures that could vaporize most materials. The probes need to function for decades in the vacuum of space, enduring cosmic rays and micrometeorite impacts, all while weighing less than a sugar packet. And communication back to Earth takes 4.37 years at light speed, meaning by the time we receive data, it's already ancient history. Critics argue Breakthrough Starshot is overly ambitious, underfunded. It's raised about $100 million so far, but estimates for full deployment run into billions. and possibly impossible with current materials science. Supporters counter that every critique was also levelled at the Apollo program, and we landed on the moon anyway. Historians still argue whether Breakthrough Starshot is a visionary leap or a billionaire's vanity project, though most agree it's at least pushing the boundaries of what's considered feasible. Second, Project Dragonfly, proposed by the Initiative for Interstellar Studies. This is a more conservative, relatively speaking, plan to send a probe to a nearby star system using laser propulsion, but with an emphasis on gradual development and international collaboration. Unlike Breakthrough Starshot's stamp-sized probes, Dragonfly envisions slightly larger spacecraft, maybe kilogram scale, capable of more sophisticated science. The mission timeline is longer, decades of ground-based testing, building incrementally more powerful lasers, launching test probes to nearby asteroids, then eventually targeting a star system. Dragonfly isn't trying to reach 20% light speed immediately, it's aiming for incremental progress. 1% light speed, then 5%, then 10%, learning from each step. The time dilation is negligible at these speeds, but the project's value is in demonstrating that humanity can organise and sustain an interstellar mission over generations. It's less about the destination and more about building the institutional infrastructure for long-term space exploration. The challenge here is political and social rather than purely technical. How do you maintain funding and public interest for a project that won't deliver results for 50 or 100 years? How do you ensure continuity when governments change, priorities shift, and the scientists who started the project retire or die before it's finished? History is littered with abandoned mega-projects, particle colliders half-built, space stations mothballed, research programs defunded when budgets tighten. Dragonfly's advocates argue that making the mission international, with buy-in from multiple nations and agencies, reduces the risk of cancellation. Critics point out that international collaborations are also vulnerable to geopolitical tensions. Look at the ISS partnership straining under US-Russia conflicts. Historians still argue whether long-term projects like Dragonfly are feasible in an era of short political cycles and shifting priorities, though examples like CERN's Large Hadron Collider, decades in development, suggest it's possible with enough institutional commitment. Third, and most speculative, are the generation ship proposals. These aren't funded or scheduled, but they're actively discussed in aerospace engineering circles. A generation ship is a massive spacecraft designed to travel for centuries, carrying a self-sustaining human population that lives, reproduces and dies aboard the ship, with only distant descendants reaching the destination. At modest sub-relativistic speeds, say 10% light speed, a journey to a star 50 light-years away takes 500 years. No time dilation to speak of, but it's still interstellar travel. The ship would need to be enormous. Artificial gravity via rotation, closed-loop ecosystems, redundant life support, onboard agriculture, medical facilities, schools, governance structures. It's less a spacecraft and more a mobile civilization, a city in a bottle hurtling through the void. The ethical questions are staggering. Is it moral to commit generations of people to a journey they didn't choose? The first-generation volunteers, but their children are born into captivity, destined to live and die in transit. Is that fair? Some philosophers argue it's no different from being born on Earth. You didn't choose your birth circumstances either. Others say it's different because Earth offers variability and possibility, while a generation ship is a fixed environment with a predetermined endpoint. There's also the risk of social collapse. 500 years is a long time. Governments rise and fall. Cultures evolve. What if the fourth generation decides the mission is pointless and mutinies, turning the ship around or shutting down life support? What if religious schisms or resource conflicts fracture the community into violence? The ship is a closed system. There's no escape, no reinforcements, no outside intervention. It's a fragile bubble of humanity alone in the dark, and history suggests that closed societies often become dystopian. Historians still argue whether generation ships are an inspiring vision of human resilience or a recipe for slow-motion catastrophe, with no clear consensus. Here's a quirky detail. In 2018, the International Academy of Astronautics published a study on the minimum viable population for a generation ship. They estimated you'd need at least 10,000 people to maintain genetic diversity and avoid inbreeding over multiple generations, plus a sperm and egg bank for additional genetic material. That's a lot of people to cram into a spacecraft, requiring massive resources, complex social structures, and ironclad governance to prevent conflict. The study concluded that generation ships are technically feasible, but socially and politically nightmarish. We can build the hardware, we're less confident about the wetware. These missions, Breakthrough Starshot, Project Dragonfly, generation ships, are humanity's first serious attempts to grapple with interstellar travel and its consequences, including time dilation. They're not going to send someone forward a century, not yet, but they're laying the groundwork, proving concepts, developing technologies. If Breakthrough Starshot succeeds and we get data from Alpha Centauri, the next mission will be bolder. Bigger probes, higher speeds, maybe even crewed missions. If Dragonfly demonstrates long-term international collaboration, it paves the way for century-spanning projects. If generation ships are ever built, they'll be test beds for closed-loop societies and multi-generational governance, skills we'd need for any long-term spacefaring civilization. The physics is settled. Time dilation is real, measurable, waiting. These missions are the first fumbling steps toward exploiting it, toward becoming a species that doesn't just live in time but navigates through it, skipping forward in measured hops, leaving the past behind like breadcrumbs scattered across the light years. It's beginning, slowly, expensively, uncertainly, but it's beginning. So here we are, you and me, at the end of this long, winding journey through the physics, the paradoxes, the heartbreak, and the possibility of time travel. And here's the thing you might not have fully appreciated until now. You're already a time traveler. Right now, this very moment, you're moving through time differently than someone else, somewhere else. It's not dramatic. You're not aging decades slower than your friends. But you're experiencing time at a rate that's measurably, verifiably different from someone at a different altitude, or moving at a different velocity, or sitting deeper in a gravitational well. The universe is keeping separate clocks for each of us, and those clocks don't quite agree. You've been time traveling your entire life. You just never notice because the differences are so small, because everyone around you is time traveling too, and because we've built our world to ignore the tiny relativistic shifts that are always present, always ticking away in the background. Every time you've flown in an airplane, you've time travelled forward, infinitesimally, but measurably. The velocity of the plane slowed your clock by nanoseconds, while the reduced gravity at cruising altitude sped it up by slightly more, resulting in a net gain of a few nanoseconds relative to someone on the ground. You aged a tiny bit faster than your friend who stayed home. Every time you've climbed a mountain or a tall building, you've time travelled forward by spending time in weaker gravity, where your clock ticks faster. Every time you've driven a car, jogged, even walked, you've altered your temporal flow relative to someone sitting still. The effects are absurdly small, nanoseconds, picoseconds, utterly negligible in any practical sense. But they're real. They're happening. The universe is constantly accounting for your motion and your position, adjusting your clock accordingly, and you're oblivious because the human brain didn't evolve to notice nanosecond differences, but atomic clocks notice. GPS satellites notice. The universe notices. Here's a thought experiment. Over your lifetime, let's say 80 years, you've taken dozens of flights, climbed countless stairs, driven thousands of miles, maybe visited high-altitude cities or low-altitude coastlines. All of those experiences have shifted your clock relative to someone who lived in a single location at sea level and never travelled. The cumulative effect might be microseconds, millionths of a second, of time dilation. You've aged microseconds less, or more, depending on the balance of velocity and altitude effects, than that stationary person. It's nothing. It's meaningless. You'll never notice it, never feel it, never benefit or suffer from it. But it's there, documented in the structure of space-time, a record of your motion through the universe. You're a time traveller on the smallest possible scale, and so is everyone else. We're all experiencing time at slightly different rates, our clocks perpetually out of sync by undetectable amounts, and we go about our lives pretending time is universal and uniform because the differences are too small to matter. But scale it up. Imagine humanity builds those relativistic spacecraft we've been discussing. Imagine missions to Proxima Centauri at 90% light speed, to distant exoplanets at 99% light speed, to the Andromeda Galaxy at 99.9999% light speed. Suddenly, the tiny relativistic effects you've been experiencing your whole life become grotesquely magnified. The astronaut who ages 10 years while Earth ages 100 isn't doing anything fundamentally different from you boarding an airplane. They're just moving faster, experiencing more velocity-based time dilation. The physics is identical. The scale is different. And that means the time travel you've been doing casually, unconsciously, your entire life is the same phenomenon that could someday send someone centuries into the future. It's not a different kind of time travel. It's the same mechanism turned up to 11. You're already part of this story. You're already a participant in the relativistic universe. You just haven't pushed the limits yet. Some physicists argue that this ubiquity of time dilation, the fact that it's always happening everywhere to everyone, is one of relativity's most underappreciated insights. We think of time travel as exotic, something requiring wormholes or black holes or impossible machines. But relativity says, no, you're doing it right now. Every moment of motion, every shift in altitude, every breath you take in a gravitational field slightly different from someone else's. It's all time travel. The universe doesn't distinguish between the mundane and the dramatic. It's all the same physics, the same curvature of space-time, the same Lorentz transformations and gravitational potentials. You're not separate from the relativistic effects we've been exploring. You're embedded in them. You're made of them. Your existence is a continuous, ongoing act of time travel through a universe where time is flexible, where simultaneity is relative, where your now and someone else's now don't quite align. That's not science fiction. That's Tuesday. Here's a quirky, almost poetic detail. Photons, particles of light, don't experience time at all. From a photon's perspective, a phrase physicists hate but tolerate for illustrative purposes, its journey from the sun to your eye, 8 light minutes in our reference frame, takes 0 time. The photon is emitted and absorbed in the same instant from its own frame. It's timeless, existing outside the flow of temporal experience. You, on the other hand, are made of matter, which means you're chained to time, you experience duration, you age, but the closer you move to light speed, the closer you approach the photon's timeless existence. At 99.9999% light speed, your clock slows so dramatically that you're almost living in the eternal now, like a photon, while the universe outside races forward in fast motion. You can never quite reach light speed, your mass forbids it, but you can asymptotically approach timelessness. There's something haunting about that. The faster you go, the more you escape time's grip, until at the cosmic speed limit, Time itself would stop for you if only the universe would let you cross that final threshold. But it won't. You're stuck in time, but you can slow it down, stretch it out, bend it to your will, within limits. And here's your place in the time-dilated universe. You're a fleeting arrangement of matter and energy, moving through space-time on a trajectory that's uniquely yours. Your clock ticks at a rate determined by your velocity and your depth in gravitational wells, and that rate is different, however slightly, from everyone else's. You share this planet with 8 billion people, and every single one of them is experiencing time at a fractionally different pace. Your now is a thin slice of space-time that doesn't quite overlap with anyone else's now, and yet we manage to coordinate, to communicate, to live together, because the differences are negligible. But they're there. The universe is keeping separate time for each of us, and someday, if we build the ships, those differences will become impossible to ignore. Someone will leave and age slowly while we age quickly, and the comfortable illusion of shared time will shatter. We'll confront the reality that time is personal, local, and negotiable, and maybe that's terrifying, or maybe it's liberating. Maybe it means we're more alone than we thought, each of us locked in our own temporal reference frame. Or maybe it means we're part of something larger, a universe where time is just another dimension to explore, bend, and navigate. You're already a time traveller. You always have been. The universe has been dilating your clock, warping your experience of duration, every single moment of your existence. You've just been travelling so slowly that you never noticed. But the potential is there, written into the fabric of space-time, waiting for you, or someone like you, to push harder, move faster, venture farther. To take the trip that turns hours into years, seconds into decades, a lifetime into a blink. The physics is settled. The universe is permissive. The only question left is whether you're brave enough or lonely enough or curious enough to step aboard, to leave everything behind, and to leap forward into a future that won't remember you. The stars are waiting, time is waiting, and you, whether you realise it or not, are already on your way. And that's where we'll leave it tonight. Out here among the stars, among the equations, among the impossible choices, and the beautiful, terrible mathematics of a universe that lets you slip through time if you're willing to pay the price. You've journeyed with me through Einstein's equations, through the tragedy of temporal displacement, through the cold logistics of building a time machine, and the warm horror of using one. You've seen the muons raining down from the atmosphere, living impossibly long because they're moving impossibly fast. You've watched GPS satellites age microseconds ahead, ticking out of sync, corrected by relativistic calculations running silently in your phone. You've stood at the event horizon of a black hole where time bends so severely that hours become years, and you've imagined, maybe with excitement, maybe with dread, boarding a ship that would carry you forward into a future where everyone you know is gone. Time dilation is real, it's measurable, it's waiting, and whether humanity ever builds the ships or not, whether we ever send someone on that one-way journey into the future, the fact remains, the universe permits it. The cosmos has written the rules in space-time's geometry, and those rules say you can skip forward, you can steal years from yourself and give them to the world outside, you can become a ghost in your own timeline. The physics is indifferent. It doesn't care about your heartbreak, your loneliness, your longing to go home. It just calculates precisely and eternally how much time you'll lose and how much the universe will gain. So rest now. Let these ideas settle, these strange truths about time's flexibility, about your place in a relativistic cosmos. Close your eyes, breathe slowly, and remember, you're already travelling through time right now, tick by tick, second by second, moving forward into a future that's unwritten but approaching. We all are. That's the one trip we're all taking together, at nearly the same speed through a universe that bends time but never breaks it. Sweet dreams, traveller, sweet dreams.